Long before the James Webb Space Telescope ever opened its mirrors in space, most cosmologists believe they already knew what it would find. Webb was designed during a period when the Big Bang model was considered remarkably successful. Observations of cosmic expansion, the cosmic microwave background, and large-scale galaxy distribution all fit neatly within a framework that had been refined for decades. The new telescope was expected to sharpen details, not disrupt foundations. In planning documents, scientific proposals, and mission briefings, Webb's role was described as confirmatory, to push existing theories to earlier times, not to rewrite them. Before Webb launched, astronomers expected faint, tiny, and chaotic early galaxies, forming slowly over hundreds of millions of years. Heavy elements and massive black holes were thought to be rare or absent. If you're fascinated by the mysteries of distant worlds and the search for life beyond Earth, subscribe now. Our journey to uncover the cosmos's hidden secrets begins today. The telescope itself was engineered specifically to look back toward the earliest chapters of cosmic history. Its 6.5-meter segmented mirror, composed of 18 hexagonal beryllium segments coated in gold, was more than twice the diameter of Hubble's primary mirror. This design increased its light-gathering power by over 6 times. The decision to focus on infrared wavelengths was deliberate. As the universe expands, light from distant galaxies stretches, shifting from ultraviolet and visible wavelengths into the infrared. Webb was built to capture light with wavelengths ranging roughly from 0.6 to 28 microns, allowing it to detect objects far beyond the reach of earlier space telescopes. Webb's scientific instruments were tailored to exploit this capability. NIRCam was designed to image faint galaxies at extreme distances with unprecedented clarity. NIRSpec could observe up to hundreds of objects simultaneously, breaking their light into spectra that revealed distances, chemical composition, and motion. MIRI extended Webb's reach into mid-infrared wavelengths, enabling the study of dust-enshrouded regions and cooler cosmic structures. Together, these instruments formed a system capable of probing the universe when it was only a few percent of its current age. Under the standard Big Bang framework, the early universe followed a carefully defined sequence. After roughly 380,000 years, the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely. This event produced the cosmic microwave background radiation, observed today at a temperature of about 2.7 Kelvin. What followed was a prolonged period during which no stars or galaxies had yet formed. During these cosmic dark ages, matter was distributed almost uniformly, with only slight density fluctuations seeded during inflation. Gravity gradually amplified those fluctuations. Dark matter, which does not interact with light but dominates the universe's mass budget, began collapsing into halos. Gas fell into these halos, slowly cooling and eventually igniting the first stars. Simulations suggested this process was inefficient and time-consuming. The earliest galaxies were expected to be small collections of stars, with irregular shapes and low luminosities. According to widely used models, it should have taken hundreds of millions of years for galaxies to accumulate enough mass to become prominent. This theoretical picture guided decades of observation planning. NASA, the European Space Agency, and the Canadian Space Agency all framed Webb's mission around refining this timeline. Early science programs prioritized measuring the faint end of the galaxy luminosity function, identifying the transition from population 3 stars to later generations, and mapping the reionization of the intergalactic medium. These goals assumed that the Big Bang model's basic chronology was sound and only required higher resolution data to fill in missing details. Before Webb's launch, dozens of research teams published predictions about what the telescope should observe. Many papers focused on redshifts greater than 10, corresponding to times when the universe was less than 500 million years old. Based on existing data and simulations, astronomers expected to find relatively few galaxies at these distances, and those that existed were predicted to have stellar masses no greater than a few hundred million solar masses. None of these forecasts suggested the presence of large, well-organized systems so early in cosmic history. When Webb launched on the 25th of December 2021 aboard an Ariane 5 rocket from French Guiana, the scientific community viewed it as the culmination of more than 2 decades of planning. Over the following 6 months, Webb traveled to the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth. There, it deployed its 5-layer sunshield, roughly the size of a tennis court, designed to block heat from the Sun, Earth, and Moon. The telescope's instruments cooled passively to temperatures necessary for infrared observation, with MIRI reaching even lower temperatures using a dedicated cryocooler. Each deployment milestone was met with relief and growing anticipation. Engineers aligned the mirror segments with nanometer precision, transforming 18 individual mirrors into a single optical surface. Calibration tests showed the instruments performing at or above expectations. From a technical standpoint, Webb appeared ready to deliver exactly what scientists had predicted. The selection of Webb's first observing targets reflected this confidence. Early deep field observations focused on regions like SMACS 0723 and other well-studied galaxy clusters. These fields had extensive archival data from Hubble and Spitzer, providing a baseline against which Webb's improvements could be measured. Astronomers expected to see the same galaxies in greater detail and to detect slightly fainter ones just beyond previous limits. The underlying assumption was that Webb would extend known trends, not overturn them. This mindset extended to how observing time was allocated. Many early programs were designed to refine parameters rather than test extremes. Proposals emphasized reducing uncertainties in star formation rates, improving metallicity measurements, and confirming photometric redshifts with spectroscopy. These goals reflected a belief that the major outlines of cosmic history were already established. Public communication before Webb's first images reinforced this outlook. Press releases and interviews highlighted Webb as a successor to Hubble, not a challenger to cosmology. The language focused on clarity, resolution, and depth. Even when scientists spoke about first light or cosmic dawn, they framed it as a period whose basic properties were already understood in outline. This confidence was rooted in the success of earlier missions. Measurements of the cosmic microwave background by QOBE in the early 1990s, followed by WMAP and later Planck, had constrained key cosmological parameters with remarkable precision. These missions determined the universe's age to be about 13.8 billion years, measured the relative proportions of normal matter, dark matter, and dark energy, and mapped tiny temperature fluctuations that matched predictions from inflationary models. Large galaxy surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, further reinforced the consistency between observation and theory on large scales. Hubble's deepest images also contributed to this sense of stability. The Hubble Ultra Deep Field revealed thousands of galaxies spanning billions of years of cosmic time. While these observations hinted at rapid early star formation, they did not clearly contradict existing models. Instead, they seemed to confirm that galaxies grew gradually through mergers and sustained star formation. Webb was therefore seen as the final observational leap needed to close the remaining gaps. Its infrared sensitivity was expected to reveal the faintest galaxies at the highest redshifts, filling in the early end of the timeline. Astronomers anticipated confirming that galaxy formation proceeded slowly and hierarchically, just as simulations predicted. What few fully appreciated was how little direct observational evidence existed for the universe's first few 100 million years. Much of what scientists believed about that era was based on extrapolation rather than direct detection. Webb's sensitivity represented not just an incremental improvement, but a qualitative shift. It allowed astronomers to detect light that had been stretched and dimmed beyond the reach of all previous telescopes. By the time Webb's instruments were fully calibrated in mid-2022, observation schedules were packed and analysis pipelines were ready. Teams around the world prepared to compare real data against long-standing predictions. The expectation remained that discrepancies, if any, would be minor and easily resolved with modest adjustments to existing models. Instead, Webb began returning images and spectra that differed from several pre-launch predictions. Early observations reported galaxies detected at higher redshifts than anticipated, with measured luminosities exceeding values commonly produced in simulations. Some systems showed inferred stellar masses and sizes larger than expected for their estimated cosmic age. These findings were documented in early Webb observing programs and follow-up analyses, prompting further observational campaigns and revisions to modeling assumptions used in galaxy formation simulations. The observations that appeared almost immediately. When the James Webb Space Telescope began returning usable scientific data in the summer of 2022, the pace of discovery was faster than many researchers expected. Within weeks of calibration, Webb was already producing deep-field images and preliminary spectra that pushed beyond the limits of all previous observation. These early datasets were not fringe experiments or speculative programs. They came from carefully planned early release observations and guaranteed time programs designed to demonstrate Webb's capabilities using well-understood targets. One of the first public images, taken in July 2022, focused on the galaxy cluster SMACS 0723. The exposure time was less than 13 hours, yet the image revealed thousands of galaxies, many of them faint and distant. Some appeared as elongated arcs due to gravitational lensing, while others were compact points of light scattered across the field. Astronomers immediately noticed something unusual. The number of faint red objects far exceeded expectations. Even accounting for lensing effects, there appeared to be an overabundance of potential high redshift galaxies. These initial impressions were not based on visual appearance alone. Teams quickly began analyzing the brightness and colors of the objects using photometric techniques. By measuring how much light each galaxy emitted in different infrared filters, researchers estimated their redshifts. Several candidates appeared to lie at redshifts above 10, and some were flagged as possible redshift 12 or even 13 objects. That placed them within the first 300 to 400 million years of cosmic history. While photometric estimates can be uncertain, the sheer number of such candidates was unexpected. What drew particular attention was not just how many early galaxy candidates Webb detected, but how bright some of them were. According to pre-launch models, galaxies at such extreme distances should have been extremely faint, requiring long exposures and strong lensing to detect. Instead, Webb was finding objects that were bright enough to stand out clearly even in relatively short observations. Some of these galaxies appeared several times more luminous than predicted for their inferred age. By August and September of 2022, multiple research groups began submitting preprints to online archives detailing these findings. Papers led by teams from institutions such as the University of Texas, Princeton, and the University of Cambridge independently reported an excess of massive galaxy candidates at high redshift. Estimates of stellar mass based on spectral energy distributions suggested values approaching or exceeding 1 billion solar masses in some cases. Under standard assumptions, assembling that much stellar mass so quickly posed a serious challenge. Spectroscopic follow-up soon added another layer of complexity. Webb's NIRSPEC instrument was used to obtain spectra for a subset of early galaxy candidates. Spectroscopy provides far more reliable redshift measurements than photometry, as it identifies specific emission or absorption features shifted by cosmic expansion. In several cases, spectroscopic redshifts confirmed that galaxies previously flagged as extreme candidates were indeed located at redshifts above 8 or 9. While not all photometric estimates held up, enough confirmations remained to sustain concern. One of the earliest spectroscopically confirmed galaxies, observed as part of the CERS survey, was located at a redshift of approximately 8.7. That placed it roughly 600 million years after the beginning of cosmic expansion. The galaxy's inferred stellar mass and brightness were already near the upper end of what models allowed at that time. Additional confirmed objects soon followed, reinforcing the pattern rather than resolving it. At the same time, Webb began detecting galaxies with unexpectedly smooth structures. Instead of the chaotic, clumpy appearance predicted for early systems, some galaxies appeared compact and well-organized. While resolution limits and lensing effects complicate morphological interpretation, the data suggested that some early galaxies had already undergone significant internal evolution. The speed at which these results emerged was striking. Previous telescopes required years to accumulate comparable evidence, often at the edge of detectability. Webb delivered it within months. By late 2022, conference presentations and workshops were filled with slides showing number counts of high redshift galaxies exceeding theoretical curves. The language used by researchers shifted subtly but noticeably. Terms like mild tension and unexpected abundance began appearing more frequently. Importantly, these observations were not confined to a single survey or research group. Independent programs using different fields of view and analysis pipelines reported similar trends. The JWST Advanced Deep Extragalactic Survey, the Cosmic Evolution Early Release Science Program, and other initiatives all found more early galaxies than expected. This convergence reduced the likelihood that the results were due to a single methodological error. Attempts to attribute the discrepancy to observational bias were explored immediately. Astronomers examined whether gravitational lensing was amplifying galaxy brightness more than anticipated, potentially making objects appear more massive than they truly were. While lensing certainly played a role in some fields, it could not account for the excess across unlensed regions. Others suggested that dust could redden galaxies, making them appear older or more distant. However, detailed modelling showed that dust alone could not fully mimic the observed colours and luminosities. Another possibility was that stellar populations in early galaxies were different from those assumed in models. If early stars were more massive or more efficient at producing light, galaxies could appear brighter without containing as much mass. Some teams adjusted their assumptions accordingly, but even aggressive changes failed to reconcile the brightest objects with standard timeline. By early 2023, the discussion had moved beyond whether the data were real. The focus shifted to what the data implied. Galaxy number density plots showed deviations at redshifts above 8 that grew larger with increasing distance. In some bins, observed galaxy counts exceeded predictions by factors of 5 to 10. While uncertainties remained large, the trend was difficult to ignore. The rapid release of Webb data also meant rapid scrutiny. Teams cross-checked each other's work, reanalyzed datasets, and challenged assumptions. Some early extreme candidates were revised downward after improved calibration or deeper observations. Yet even after these corrections, a substantial excess of early galaxies persisted. The problem did not disappear with better data. It became more clearly defined. These observations were obtained early in Webb's operational phase, before many comparison models had been updated to reflect its increased sensitivity. A number of commonly used galaxy formation models had been calibrated primarily using data from Hubble and earlier infrared surveys. Webb's observations extended measurements into higher redshift regimes that had not previously been sampled with comparable depth. As a result, differences between model predictions and observed galaxy counts were documented directly in published plots, tabulated measurements, and spectroscopically confirmed sources. As additional datasets were collected, analyses continued to identify galaxies at high redshift with luminosities and inferred growth rates higher than those typically produced in pre-existing simulations. These galaxies were detected at epochs close to the onset of large-scale structure formation. The observations prompted multiple studies examining whether revisions to star formation efficiency, feedback processes, or halo growth rates could account for the measured properties within existing theoretical frameworks. The initial Webb observations prompted a concentrated period of follow-up analysis and theoretical reassessment. Researchers investigated whether discrepancies arose from measurement uncertainties, modeling assumptions, or limitations in existing simulations of early galaxy formation. Subsequent studies focused on refining observational techniques, expanding survey areas, and updating theoretical models to better match the properties of the observed high redshift galaxy population. The earliest galaxies were not supposed to look like this. As researchers moved beyond raw counts and redshift confirmations, attention shifted toward what these early galaxies actually looked like. This was where expectations began to unravel more visibly. For decades, theoretical models had described the first galaxies as disordered and fragile systems. They were expected to be dominated by turbulent gas, shaped by frequent mergers, and lacking any stable internal structure. Webb's images, however, presented a different picture, one that became harder to dismiss as more data arrived. High-resolution imaging from NIRCam allowed astronomers to examine the shapes and light distributions of galaxies at redshifts above 7 with a clarity never achieved before. Instead of the diffuse, irregular smudges anticipated by simulations, several early galaxies appeared compact and centrally concentrated. Some showed smooth light profiles, suggesting that stars were already organized into coherent systems. In a few cases, researchers even noted hints of flattened or disk-like structures, something models predicted would not emerge until much later. One of the most discussed early examples came from the CERS field, where a galaxy at redshift near 8 displayed a remarkably compact morphology with a bright core. Its half-light radius was measured at less than 500 parsecs, indicating that a large fraction of its stars were packed into a small volume. For comparison, local dwarf galaxies with similar masses tend to be more diffuse. The implication was not just early formation, but efficient organization. Surface brightness measurements added to the tension. These galaxies were not only compact, they were luminous. Their ultraviolet light output suggested dense stellar populations forming in a coordinated way. In standard models, early star formation is expected to be bursty and inefficient, with feedback from supernovae disrupting gas clouds before they can settle. Webb's observations hinted that some early systems either resisted this disruption or recovered from it quickly. Astronomers also examined how light was distributed across different wavelengths. By comparing images taken in multiple infrared filters, they could infer whether stars were spread evenly or concentrated toward galactic centers. Several high redshift galaxies showed steep brightness gradients, a feature associated with more mature systems. This was unexpected at epochs when the universe was less than 1 billion years old. These findings were not isolated. Similar structural characteristics appeared across different surveys and sky regions. The JWST Advanced Deep Extragalactic Survey and the GLAS program both reported early galaxies with compact, regular appearances. The consistency across independent datasets reduced the likelihood that these features were artifacts of image processing or lensing distortions. The issue became more pronounced when researchers compared Webb's observations directly with simulated galaxies at the same redshift. In many simulations, early galaxies appear clumpy, asymmetric, and extended. star-forming regions are scattered, and gas dominates the visible structure. When these simulated images were degraded to match Webb's resolution and noise characteristics, they still failed to reproduce the smoothness seen in real data. The mismatch was not subtle. Another unexpected feature was the apparent alignment of stellar populations. In some galaxies, light profiles suggested that stars formed in relatively short, intense episodes rather than prolonged, chaotic bursts. This implied a level of coordination in gas inflow and cooling that models struggled to explain. Gas in the early universe was expected to be hot, metal-poor, and easily disrupted. Webb's galaxies suggested otherwise. The presence of dust added further complexity. Infrared observations indicated that some early galaxies contained enough dust to affect their observed colors and brightness. Dust formation requires previous generations of stars to produce heavy elements and expel them into the interstellar medium. The detection of dust implied that multiple cycles of star formation and stellar death had already occurred. Structurally, this dust appeared to be distributed in a way that suggested internal organization rather than random dispersion. Researchers began to quantify these discrepancies using size-mass relations. When plotted against stellar mass, many early galaxies fell below the size predictions of standard models, meaning they were too small for their inferred mass. This placed them closer to the compact galaxies observed at later cosmic times, rather than the diffuse systems expected near cosmic dawn. The implication was that these galaxies had either formed stars more efficiently or assembled mass through processes not fully captured in simulations. The morphology problem also intersected with kinematic expectations. While direct measurements of rotation were challenging at such distances, indirect indicators suggested that gas and stars might already be moving in coordinated patterns. If confirmed, this would imply that angular momentum had been redistributed rapidly, allowing early galaxies to settle into stable configurations sooner than predicted. Efforts to explain these observations within existing frameworks multiplied. Some researchers proposed that early galaxies formed in exceptionally dense regions of the universe, accelerating their evolution. Others suggested that feedback from the first stars might have been less disruptive than assumed, allowing gas to remain bound and organized. There were also suggestions that the initial conditions used in simulations underestimated the clumpiness of matter on small scales. Despite these attempts, no single adjustment resolved all aspects of the problem. Increasing star formation efficiency could help explain brightness, but not compactness. Altering feedback prescriptions might preserve structure, but then overproduce stars. Each fix introduced new inconsistencies elsewhere. The visual evidence from Webb was forcing astronomers to confront the possibility that early galaxy formation followed pathways more varied and efficient than models allowed. The debate intensified as more detailed analyses were published. Papers began, including side-by-side comparisons of observed and simulated galaxies, highlighting structural differences. Conference talks featured animations showing how simulated galaxies evolved compared to Webb's static snapshots. The contrast was difficult to ignore. The structural measurements of early galaxies were analyzed in terms of gravitational dynamics, gas cooling, and stellar feedback processes. Observed differences between galaxy morphology and predictions prompted further study into how these physical processes operated under the conditions of the early universe. As Webb continued observing, the catalogue of early galaxies expanded, including both irregular systems consistent with prior models and compact, organized galaxies that differed from predictions. These observations were documented quantitatively, providing a range of morphological properties across different redshifts. By the end of Webb's first year of observations, analyses included both galaxy counts and internal structural measurements. The data showed that many early galaxies exhibited compact and organized morphologies, differing from the more diffuse, clumpy structures commonly produced in simulations. Researchers incorporated these measurements into comparisons with theoretical models. How old the universe was when these objects existed. The redshifts measured by Webb do more than locate galaxies in space. They place them precisely in cosmic time. Cosmologists convert redshift into age, using the universe's expansion history, which is defined by the Hubble constant, matter density, and dark energy contribution. For decades, precise measurements from missions such as WMAP and Planck had constrained the current expansion rate at roughly 67.4 kilometers per second per megaparsec, giving the universe an age of about 13.8 billion years. Within this framework, the earliest stages of galaxy formation were thought to be strictly limited by the time available since the Big Bang. The standard timeline predicts that cosmic recombination occurred around 380,000 years after the Big Bang, producing the cosmic microwave background observed today. Following this, the universe entered a dark age, lasting roughly 100 to 200 million years, during which no luminous objects existed, only diffuse neutral hydrogen. Star formation is believed to have started gradually after this period, with the first population 3 stars appearing around 250 million years post-Big Bang. These stars, composed entirely of primordial hydrogen and helium, were short-lived but essential for producing the first heavy elements. Webb's detections, however, place many galaxies at redshifts, corresponding to only 300 to 400 million years after the Big Bang. In some cases, candidates at redshift 12 to 13 imply that these galaxies existed when the universe was barely 330 to 350 million years old. This leaves a remarkably narrow window for structure formation, compressing the time for gas to collapse, stars to ignite, and galaxies to assemble into the massive and organized systems Webb observed. In comparison, previous models had expected the first detectable galaxies to emerge no earlier than roughly 500 million years after the Big Bang, with most large systems forming closer to 700–800 million years. The calculation is grounded in the cosmological parameters derived from Planck 2018 data. Matter density, omega m of approximately 0.315, dark energy density, omega well, of 0.685, and a baryon fraction of roughly 0.049. Using these values, redshift can be translated into look-back time, revealing just how compressed early galaxy formation must have been. For instance, a galaxy at redshift 10 corresponds to about 480 million years post-Big Bang, while redshift 12 shrinks the available cosmic time to roughly 370 million years. These numbers leave little room for gradual assembly through hierarchical mergers and incremental star formation, which are central assumptions in the standard LCDM model. Time constraints become even more acute when considering stellar population ages. Spectral energy distribution fitting suggests that some of Webb's earliest galaxies already contain stars with inferred ages of 50 to 100 million years at redshift 1012. In other words, these stars must have formed within the first 250 to 300 million years of cosmic history, implying star formation began almost immediately after the end of the cosmic dark ages. For context, simulations from projects like Illustris TNG and Blue Tides had predicted that such massive early galaxies would not appear until several 100 million years later, creating a pronounced tension with the observed timing. The speed of assembly implied by these age estimates is extraordinary. Galaxies appear to have gathered significant baryonic mass within only a few dynamical times of their host dark matter halos. In standard models, gas cooling and collapse are limited by radiative cooling rates, feedback from early supernovae, and the inefficiency of star formation in low metallicity environments. Yet Webb's data suggests that in several cases, galaxies achieved stellar masses approaching 9 solar masses within 300–400 million years. Such rapid growth pushes the limits of physically plausible star formation efficiencies, as constrained by observed gas-to-star conversion rates in the local universe and high redshift simulations. The presence of mature stellar populations at these ages also carries implications for nucleosynthesis. Heavy elements, such as oxygen and carbon, detected through Webb's NIRSPEC spectroscopy, require multiple generations of star formation and supernova enrichment. If galaxies already exhibit substantial metallicity at redshifts above 10, this indicates that the initial stars formed, evolved, and exploded on compressed timescales, enriching subsequent stellar generations within tens of millions of years. Another factor, compounding the timeline pressure, is the growth of dark matter halos. Halos provide the gravitational scaffolding necessary for baryonic matter to collapse and form stars. CDM simulations predict that the earliest massive halos, capable of hosting galaxies above 10·9 solar masses, become common only around redshift 6 to 8. Webb's observations of massive systems at redshifts 10-12 imply either an underestimation of early halo formation rates or an unusually efficient conversion of halo mass into luminous stars. Either scenario requires a recalibration of key parameters in cosmic structure models. The cosmological implications extend to reionization as well. The epoch of reionization is believed to have begun around redshift 1520 and completed by redshift 6. The abundance and luminosity of early galaxies observed by Webb suggests that these systems contributed significantly to reionizing the intergalactic medium far earlier than expected. Photons capable of ionizing hydrogen had to escape their host galaxies efficiently, implying not only early star formation, but also structural conditions that allowed radiation to permeate surrounding space. Webb's timeline also challenges assumptions about mergers. Hierarchical growth predicts that small halos merge progressively to form larger galaxies over hundreds of millions of years. Yet the compactness and mass of many high redshift galaxies indicate that substantial mass accumulation occurred with minimal dependence on repeated mergers. If early systems formed largely in isolation, the implication is that gas accretion, cooling, and star formation must have been remarkably rapid, operating near theoretical efficiency limits. Even individual star clusters contribute to the time compression problem. Some of Webb's data suggest that star formation in the first galaxies produced dense clusters with masses exceeding 10·6 solar masses. The formation of such clusters requires high gas densities and short freefall times, again leaving only tens of millions of years for gravitational collapse, fragmentation, and ignition of stars. Observing multiple such clusters within a single galaxy at redshift 12 implies synchronized, large-scale star formation remarkably early in cosmic history. Observational cross-checks reinforce the age calculations. Independent teams employing different photometric and spectroscopic pipelines consistently place these galaxies within the first 400 million years. Gravitational lensing corrections, instrumental calibration, and background subtraction have all been applied, and the inferred redshifts and stellar population ages remain consistent across analyses. These age constraints introduce measurable discrepancies between observed early galaxy formation and predicted timelines from standard cosmological models. If galaxies formed more quickly than expected, this affects assumptions regarding the growth of density fluctuations, baryonic cooling, and star formation efficiency. While LCDM continues to match large-scale observations, the early emergence of massive galaxies indicated by Webb data necessitates revised modeling of baryonic processes, halo growth rates, and feedback mechanisms. Small adjustments to parameters such as the Hubble constant or matter density alter the inferred timing, but do not fully account for the observed formation rates at the highest redshifts. Galaxies with more mass than the theory allows. Once the age compression problem became clear, attention shifted to a closely related issue that proved even harder to explain: the mass of these early galaxies. It was one thing for galaxies to appear early. It was another for them to already contain enormous amounts of matter. Webb's observations indicated that many high redshift systems were not marginal or barely assembled objects. They were already massive, in some cases rivaling galaxies that were previously thought to require billions of years to build. Stellar mass estimates rely on careful analysis of a galaxy's light across multiple wavelengths. Webb's infrared coverage allowed astronomers to sample rest frame optical light from galaxies at extreme redshifts, something no previous telescope could do. This is critical because optical light traces older, lower mass stars that dominate a galaxy's total mass. Using spectral energy distribution fitting, teams could infer how much stellar material was already present, rather than relying solely on ultraviolet light from young stars. The results were striking. Several galaxies observed at redshifts between 8 and 12 showed inferred stellar masses between 500 million and 2 billion solar masses. In one widely discussed case from the CEERS survey, a galaxy at redshift near 9 was estimated to contain more than 1 billion solar masses in stars. Under standard assumptions, this implied that a substantial fraction of all available baryonic matter in its host dark matter halo had already been converted into stars. This created immediate tension with theoretical limits. In well-CDM cosmology, baryons make up only about 16% of the total matter content, with the rest dominated by dark matter. Not all baryons are expected to cool and form stars. Feedback processes such as radiation pressure, stellar winds, and supernova explosions eject gas and suppress star formation. Even in optimistic models, converting more than 10 to 15% of available baryons into stars at such early times was considered difficult. Webb's galaxies appeared to exceed these limits. The implied dark matter halos required to host such massive stellar systems were also problematic. A galaxy with a stellar mass of 1 billion solar masses would typically be expected to reside in a halo of at least 10 to 20 billion solar masses. Simulations predict that halos of this size should be extremely rare at redshifts above 10. Yet Webb was finding multiple candidates across independent fields. The statistical improbability of encountering so many massive halos so early raised concerns that the underlying growth rate of structure might be underestimated. Researchers examined whether the stellar masses could be overestimated. One possibility was that assumptions about stellar populations were incorrect. If early stars were unusually massive and luminous, they could produce more light per unit mass, making galaxies appear heavier than they truly were. Some teams explored top-heavy initial mass functions to test this idea. While such adjustments reduced mass estimates modestly, they did not eliminate the discrepancy. Many galaxies remained too massive, even under extreme assumptions. Another consideration was the contribution of nebular emission lines. Strong emission from ionized gas can contaminate broadband photometry, artificially inflating inferred stellar masses. Webb's spectroscopic capabilities allowed astronomers to correct for this effect more accurately than before. In several cases, applying these corrections lowered mass estimates by 20 to 30%. However, even after these adjustments, a significant number of galaxies still exceeded expected mass limits for their age. The mass problem also intersected with observations of galaxy compactness. Many of these early systems packed their stellar mass into very small volumes. High surface mass densities suggested intense gravitational binding and efficient gas inflow. In standard models, such dense configurations are more typical of later epochs, after repeated mergers and long periods of accretion. Seeing them so early implied that mass assembly mechanisms were operating at near maximum efficiency. Comparisons with cosmological simulations highlighted the scale of the issue. Large volume simulations, such as Illustris TNG, Eagle, and Simba, predict that galaxies with stellar masses above 10, 9 solar masses should be exceedingly rare at redshifts above 8. When Webb's observed mass functions were plotted against simulated predictions, the observed values exceeded expectations by factors of 3 to 10, depending on redshift and mass bin. These were not minor deviations that could be smoothed out by uncertainty. They represented a systematic offset. The problem became even more acute when researchers considered the growth history implied by these masses. If a galaxy contained 1 billion solar masses in stars at redshift 10, it must have formed stars at an average rate of several solar masses per year over its entire existence. Given that star formation likely did not begin immediately at the Big Bang, the effective rate would have had to be even higher. Such sustained activity strains assumptions about gas supply, cooling efficiency, and feedback regulation. Gas accretion rates were another limiting factor. Galaxies grow by pulling gas from their surroundings, but the inflow rate is constrained by the mass of the halo and the density of the intergalactic medium. At early times, gas was hotter and more diffuse, making rapid accretion difficult. Yet the masses inferred from Webb data suggested that galaxies somehow overcame these barriers, assembling and retaining gas at exceptional rates. Some researchers proposed that cold gas streams might have fed early galaxies more efficiently than simulations predicted. In this scenario, dense filaments of gas could penetrate hot halos and deliver fuel directly to galactic centers. While this mechanism exists in simulations, it was not thought to be sufficient to explain the observed masses at such early times. Enhancing its efficiency enough to match Webb's data required pushing parameters beyond commonly accepted ranges. Gravitational lensing was again scrutinized as a potential explanation. If galaxies were magnified more than expected, their luminosities and inferred masses could be overestimated. Detailed lens modeling, however, showed that most of the massive candidates were either weakly lensed or not lensed at all. Lensing could explain individual cases, but not the population as a whole. The mass discrepancy can be examined in the context of cosmic star formation history. Integrating observed stellar mass densities at high redshift indicates higher than expected stellar mass buildup during the first billion years. This differs from established reconstructions of star formation over cosmic time, which show a gradual rise toward a peak several billion years after the Big Bang, followed by a decline at later epochs. These mass estimates were derived using multiple analysis techniques. Independent teams applying different models, priors, and fitting methods reported broadly similar stellar mass values for high redshift galaxies. The agreement across methodologies reduced the likelihood that the inferred masses resulted from a single modeling assumption or data processing approach. Higher than expected galaxy masses at early times affect modeled processes such as heating of the intergalactic medium, the timing and intensity of reionization, and subsequent structure formation. Galaxies with large stellar masses produce increased radiation, mechanical feedback, and metal enrichment, all of which influence surrounding gas and later galaxy evolution. By the end of 2023, observational evidence indicated that massive galaxies existed at significantly earlier epochs than predicted by standard models. The inferred stellar masses, when considered alongside compressed formation timescales, place tight constraints on allowable growth rates, baryon conversion efficiencies, and feedback processes. These measurements require reconciliation between observed galaxy properties and existing theoretical limits. Stars forming faster than physics predicts. Once the unexpectedly high stellar masses of early galaxies were established, researchers confronted an even more demanding implication. Those stars had to form at extraordinary speeds. Mass alone was not the problem. The rate at which that mass appeared was. Webb's observations implied that early galaxies were converting gas into stars at efficiencies and speeds that pressed against, and in some cases exceeded, limits long considered physically reasonable. Star formation is governed by several bottlenecks. Gas must cool, collapse under gravity, fragment into dense regions, and ignite nuclear fusion. Each step is regulated by physical processes that impose time delays. In the early universe, these delays were expected to be especially severe. Gas was hotter, more diffuse, and largely free of heavy elements that aid cooling. Feedback from the first generations of stars was thought to further slow the process by heating surrounding gas and driving it out of shallow gravitational wells. Taken together, these constraints led to conservative estimates for early star formation rates. Webb's data challenged those estimates almost immediately. Using infrared photometry and spectroscopy, astronomers inferred star formation rates of 10 to 30 solar masses per year in some galaxies at redshifts above 8. In a few extreme cases, rates approached or exceeded 50 solar masses per year. To put that in perspective, the Milky Way today forms roughly 1 to 2 solar masses worth of stars annually. These early galaxies, despite being far smaller and younger, appeared to be forming stars at rates comparable to or greater than large modern spirals. Such rates implied rapid gas consumption. If sustained even briefly, they would exhaust available fuel in tens of millions of years. This raised immediate questions about how galaxies replenished their gas supplies. Continuous inflow from the intergalactic medium would have been required, yet models predicted that inflow rates at such early times were limited by the growth of dark matter halos and the thermal state of the surrounding gas. Spectral energy distribution modeling provided additional clues. Many early galaxies showed signs of intense recent starbursts rather than slow, continuous star formation. Their light was dominated by young stellar populations only a few million years old. This suggested that star formation was occurring in powerful, concentrated episodes rather than gradually. The intensity of these bursts implied gas densities and pressures far higher than expected for such early epochs. The problem became more pronounced when researchers combined star formation rates with stellar mass estimates. If a galaxy already contained 1 billion solar masses in stars and was still forming stars at tens of solar masses per year, its past activity must have been even more intense. Backward extrapolations implied average rates far exceeding what simulations allowed, even under optimistic assumptions. Gas cooling was a central concern. In metal-poor environments, cooling relies primarily on hydrogen and helium transitions, which are inefficient at shedding energy. Heavy elements dramatically enhance cooling by providing additional pathways for radiation. Yet Webb's star formation rates suggested that gas was cooling and collapsing efficiently very early on. This implied either that metal enrichment occurred faster than expected, or that cooling processes in primordial gas were more effective than models assumed. Some researchers revisited the role of molecular hydrogen, which can enable cooling in the absence of metals. While molecular hydrogen is fragile and easily destroyed by radiation, dense regions shielded from ultraviolet light could preserve it. Webb's observations hinted that such regions may have been more common or more resilient in the early universe than previously believed. Even so, scaling this mechanism up to galaxy-wide star formation rates remained challenging. Feedback posed another difficulty. Massive stars produce intense radiation, stellar winds, and eventually supernova explosions. In small early galaxies, these effects were expected to blow gas out and suppress further star formation. Webb's data suggested the opposite. Star formation continued vigorously, despite the presence of massive stars. This implied that feedback was either less disruptive or more localized than models predicted, allowing galaxies to retain gas and continue forming stars. Observations of ionized gas provided indirect support for this idea. Emission lines detected by NIRSPEC indicated large reservoirs of ionized hydrogen coexisting with ongoing star formation. This suggested a balance between feedback and gas inflow that maintained high star formation rates. How such a balance was achieved so early remained unclear. The efficiency of star formation also came under scrutiny. In nearby galaxies, only a small fraction of available gas is converted into stars during a given dynamical time. Webb's early galaxies appeared to convert gas far more efficiently. Estimates suggested efficiencies approaching 20 to 30% in some cases, several times higher than typical values observed today. Such efficiencies are rare even in extreme local starburst galaxies. These findings prompted researchers to examine whether the inferred star formation rates were overestimated. Dust attenuation can obscure star formation, but Webb's infrared sensitivity allowed astronomers to account for dust more accurately than before. In several cases, correcting for dust increased estimated star formation rates rather than reducing them, indicating that obscuration was not the primary driver of high inferred values. Comparisons with numerical simulations highlighted the gap. State-of-the-art simulations incorporate complex recipes for star formation and feedback, calibrated to match observations across cosmic time. When Webb's inferred rates were applied, simulations struggled to reproduce them without breaking agreement at later epochs. Increasing early star formation efficiency often resulted in too many stars overall, conflicting with observations of the present-day universe. Some theorists explored scenarios involving bursts triggered by rapid gas inflows along cosmic filaments. In this picture, early galaxies could experience short-lived but extreme star formation episodes fueled by sudden gas delivery. While plausible in principle, simulations suggested that such bursts would be brief and rare. Webb's observations implied that high star formation rates were common, not exceptional. The star formation puzzle also intersected with reionization. High rates of star formation produce large numbers of ultraviolet photons capable of ionizing hydrogen. If early galaxies were as active as Webb suggested, they could have driven reionization faster and earlier than previously modeled. This raised questions about whether reionization histories inferred from cosmic microwave background measurements needed revision. Evidence for rapid star formation was derived from multiple diagnostics. Independent indicators, including ultraviolet luminosities, emission line strengths, and inferred stellar ages, produced consistent estimates of elevated star formation activity across early galaxy samples. As discussions evolved, researchers examined how star formation processes might differ under early universe conditions. Factors such as gas turbulence, magnetic fields, and the initial distribution of density fluctuations can influence star formation rates and efficiencies. Conditions present in early galaxies may not align with assumptions used in models calibrated primarily to later cosmic epochs. When considered alongside early formation times and large stellar masses, inferred star formation rates place strong constraints on allowable physical mechanisms. Sustained star formation at tens of solar masses per year within the first few 100 million years requires high gas accretion rates, efficient cooling, and limited suppression from feedback. These combined observational constraints define the range of conditions that models must reproduce to match early galaxy properties. Unexpected chemical complexity in the early universe. By the time astronomers had grappled with how quickly early galaxies formed stars, another problem emerged that cut even deeper into established expectations. Those stars appeared to be forming in environments that were already chemically evolved. Webb's infrared spectroscopy began revealing signatures of heavy elements and dust in galaxies that existed only a few 100 million years after the Big Bang. According to long-standing models, this level of chemical complexity simply should not have been present so early. In cosmology, chemical enrichment follows a strict sequence. The Big Bang produced almost exclusively hydrogen and helium with trace amounts of lithium. Every heavier element, carbon, oxygen, silicon, iron, must be forged inside stars and dispersed through stellar winds or supernova explosions. This process takes time. The first generation of stars, known as Population 3, were expected to be massive, short-lived, and metal-free. Only after they ended their lives could the universe begin accumulating heavier elements. Webb's data suggested that this sequence unfolded far faster than anticipated. Using NIRSpec, researchers detected emission lines from ionized oxygen in galaxies at redshifts above 8. Oxygen is not produced by the first nuclear reactions after the Big Bang. It requires multiple generations of massive stars. The presence of strong oxygen lines implied that some galaxies had already experienced extensive stellar processing. In several cases, inferred metallicities reached 10 to 30% of the Sun's value. For systems existing less than 500 million years after cosmic expansion began, these numbers were startling. Carbon signatures added to the puzzle. Webb observations revealed carbon emission in multiple early galaxies, indicating that intermediate mass stars had already evolved and contributed to chemical enrichment. These stars typically live tens to hundreds of millions of years. Their presence implied that star formation must have started extremely early and proceeded continuously or in rapid succession. This left little room for the prolonged, inefficient early phase predicted by many models. Dust detection compounded the problem. Dust grains form from heavy elements expelled by stars and supernovae, and they require time to accumulate. Webb's mid-infrared observations showed dust absorption features in several high redshift galaxies, affecting their spectral energy distributions. Some galaxies displayed enough dust to significantly obscure ultraviolet light, a phenomenon thought to be rare in the early universe. The inferred dust masses, in some cases exceeding 1 million solar masses, suggested highly efficient dust production mechanisms. This raised questions about the sources of early dust. Supernovae can produce dust quickly, but much of it is expected to be destroyed by reverse shocks. Alternative sources, such as asymptotic giant branch stars, require longer lifetimes. Webb's detections implied either that dust survival rates were higher than expected, or that dust formation pathways were more efficient in early environments. Neither possibility fit neatly within existing frameworks. Chemical complexity also influenced how astronomers interpreted galaxy colors. Initially, some red colors in early galaxies were attributed to extreme redshifts alone. However, detailed modeling showed that dust reddening and metal-rich stellar populations contributed significantly. This meant that early galaxies were not just distant, they were internally complex. Their light carried the imprint of multiple generations of star formation, enriched gas, and dust-laden regions. The presence of metals had further implications for star formation. Heavy elements enhance cooling by allowing gas to radiate energy more efficiently. This makes it easier for gas clouds to collapse and form stars. Webb's detection of metals provided a partial explanation for the unexpectedly high star formation rates discussed in the previous chapter. However, it also deepened the mystery of how such enrichment occurred so quickly in the first place. Comparisons with chemical evolution models highlighted the discrepancy. Standard models predicted that reaching even 10% solar metallicity should take several hundred million years of sustained star formation. Webb's galaxies appeared to achieve this in less than half that time. Some researchers attempted to accelerate enrichment by assuming extremely top-heavy stellar populations dominated by massive stars that enrich their surroundings rapidly. While this helped marginally, it still struggled to reproduce the observed metallicities without overproducing stars. The spatial distribution of metals added another layer of complexity. In some galaxies, metal emission appeared centrally concentrated, suggesting rapid enrichment in dense cores. In others, metals seemed more evenly distributed, implying efficient mixing throughout the galaxy. Both scenarios posed challenges. Rapid central enrichment required intense early starbursts, while widespread metals implied strong outflows and turbulence capable of redistributing material on short timescales. Webb's findings also intersected with observations from other facilities. ALMA had previously detected dust and carbon in a handful of high redshift galaxies, but those detections were rare and often involved extreme objects. Webb showed that chemical complexity was not confined to a few outliers. It appeared to be common. This broadened the scope of the problem from isolated curiosities to a population-wide phenomenon. Chemical signatures also affected age estimates. Metal-rich stellar populations evolved differently from metal-poor ones, influencing the interpretation of galaxy spectra. Accounting for higher metallicity often increased inferred stellar ages, further compressing formation timelines. In some cases, fitting models suggested that star formation began less than 200 million years after the Big Bang, leaving an extraordinarily short window for initial metal-free stars to dominate. Early chemical enrichment influences modeled processes such as heating of the intergalactic medium, the efficiency of subsequent star formation, and the escape of ionizing radiation. Metals and dust absorb and reprocess photons, affecting how radiation propagates from galaxies into surrounding gas. Observations indicate that these factors must be considered when modeling early galaxy environments. Researchers also considered whether observational biases could explain the findings. Perhaps Webb was preferentially detecting chemically evolved galaxies because they are brighter and easier to observe. While selection effects undoubtedly play a role, simulations incorporating these biases still failed to match the observed abundance of metal-rich systems. The discrepancy persisted even after accounting for detection thresholds. As more spectroscopic data accumulated, multiple independent teams reported similar metallicities using different analysis techniques. Reported values were consistent across methods, indicating agreement in inferred chemical abundances. How these measurements align with existing models of cosmic chemical evolution remains under investigation. The detection of metals and dust at high redshift challenges assumptions used in models that treat the early universe as chemically simple for extended periods. Observations indicate that chemical enrichment accompanied early star formation and stellar mass buildup. As a result, early galaxies contained enriched gas and dust at earlier times than previously incorporated into many models. Observations of rapid star formation, mass assembly, and chemical enrichment raise questions about the formation timescales of other massive astrophysical objects. Data from Webb indicate that compact, luminous systems associated with accreting black holes are present at similarly early epochs, motivating further examination of growth mechanisms under early universe conditions. Black holes that should not exist yet. As evidence mounted for rapid star formation and early chemical enrichment, another class of objects emerged from Webb's observations that intensified the tension even further: massive black holes. These were not subtle hints or ambiguous signals. Webb, along with complementary data from other observatories, revealed black holes in the early universe that were already enormous, actively accreting, and energetically influencing their surroundings, at times when theory predicted they should barely have begun forming. Black holes grow through accretion and mergers, processes that are fundamentally time-limited. In standard scenarios, the first black holes form from the remnants of massive stars, typically tens of solar masses. From there, growth proceeds gradually as gas falls in or as black holes merge during galaxy interaction. Even under optimistic assumptions, growing a black hole to millions or billions of solar masses requires hundreds of millions to billions of years. Webb's data suggested that some black holes had already reached these scales within the universe's first 500 to 700 million years. Webb's infrared sensitivity allowed astronomers to identify active galactic nuclei at redshifts above 7 by detecting characteristic emission features associated with accreting black holes. Broad emission lines, high ionization signatures, and compact, extremely luminous cores indicated that these were not just small black holes flickering weakly. They were powerful engines consuming matter at substantial rates. One of the most striking cases involved a quasar observed at redshift near 7.5, corresponding to a time when the universe was roughly 700 million years old. Analysis of its luminosity suggested a central black hole mass of several hundred million solar masses. Such an object would have had to grow at or near theoretical maximum rates almost continuously since its formation. Any significant interruption would make its existence at that epoch nearly impossible under conventional growth models. Even more challenging were detections of active black holes in galaxies at redshifts above 9. While mass estimates in these cases were less certain, the inferred accretion luminosities implied black holes far larger than the stellar remnants expected from first-generation stars. Some appeared to be at least 1 million solar masses, existing when the universe was barely 500 million years old. The problem deepened when researchers examined the host galaxies. These black holes were embedded in systems that were already massive, chemically enriched, and actively forming stars. This suggested coordinated growth between galaxies and their central black holes very early in cosmic history. In later epochs, such coevolution is well established, with correlations observed between black hole mass and galaxy properties. Webb's observations implied that these relationships may have been established almost from the beginning. The idea of rapid, uninterrupted growth was quickly scrutinized. Accretion onto black holes generates radiation that pushes back against infalling gas, creating a natural limit on growth speed. Sustaining near maximal accretion for hundreds of millions of years would require a finely tuned balance between inflow and feedback. Small disruptions, such as supernova explosions or variations in gas supply, could slow growth significantly, yet Webb's black holes appeared to have overcome these obstacles. Astronomers revisited alternative formation pathways. One possibility involved direct collapse black holes, formed not from stars, but from the collapse of massive gas clouds. Such objects could begin life with masses of tens of thousands to hundreds of thousands of solar masses, providing a head start. However, direct collapse scenarios require very specific conditions: intense radiation fields to suppress star formation, low metallicity to limit cooling, and stable gas inflows. Webb's detection of metals and dust in early galaxies made these conditions harder to achieve widely. Another idea involved runaway mergers in dense star clusters, producing intermediate mass black holes that could grow rapidly. While plausible in localized environments, scaling this mechanism up to explain the observed abundance of massive early black holes remained difficult. The required cluster densities and merger efficiencies would need to be extreme. Webb's data also suggested that early black holes were not rare. Surveys covering relatively small areas of the sky detected multiple candidates, implying a higher space density than expected. When extrapolated to the full sky, these numbers exceeded predictions from models calibrated to match later quasar populations. This indicated that whatever process formed these black holes was both efficient and widespread. The spectral properties of these early active nuclei added another layer of complexity. Some showed evidence of obscuration, with dust partially blocking their emission. This implied that black hole growth was occurring in dusty, gas-rich environments, despite the challenges such conditions pose for early formation. The coexistence of dust, star formation, and black hole accretion so early suggested a tightly coupled ecosystem operating at high efficiency. X-ray observations from facilities like Chandra and XMM Newton provided supporting evidence. While their sensitivity limited detections at extreme redshifts, stacking analyses indicated excess X-ray emission consistent with accreting black holes in early galaxies. When combined with Webb's infrared data, These signals strengthened the case for a substantial population of early black holes. The growth timelines implied by these observations were unforgiving. For a black hole to reach 100 million solar masses by 700 million years after the Big Bang, it would need to accrete nearly continuously at high efficiency. Any delay in seed formation would tighten the constraints further. If seeds formed at 200 million years, the growth window shrinks dramatically, demanding near-perfect conditions. Researchers also considered whether black hole masses might be overestimated. Luminosity-based mass estimates depend on assumptions about accretion geometry and efficiency. Alternative models could reduce inferred masses somewhat, but not enough to resolve the discrepancy. Even conservative estimates left black holes far larger than expected. The implications extended to feedback. Accreting black holes release enormous energy, heating gas and potentially suppressing star formation. Yet Webb's host galaxies continued forming stars rapidly. This suggested that feedback either operated differently in early galaxies or was offset by equally strong gas inflows. Understanding this balance became another unresolved challenge. The presence of massive early black holes also influenced interpretations of reionization. Active nuclei produce hard radiation capable of ionizing helium and hydrogen. If common, they could contribute significantly to the ionizing background. Webb's detections raised the possibility that black holes played a larger role in early cosmic heating and ionization than previously assumed. As more candidates emerged, research focused on evaluating formation pathways capable of producing black holes with large inferred masses at early epochs. Observations indicated that these objects were present across multiple survey fields and redshift ranges, prompting comparison with existing cosmological growth models. These observations motivated examination of alternative black hole seeding and growth mechanisms under early universe conditions. Differences in gas dynamics, feedback efficiency, and accretion behavior relative to later epochs were considered in modeling efforts to reproduce observed black hole properties. Observations of early black holes are evaluated alongside measurements of early star formation, stellar mass assembly, and chemical enrichment. These combined datasets place constraints on the timing and efficiency of structure formation processes. Subsequent analysis examines whether predicted dark matter halo growth rates are consistent with the properties of early galaxies and black holes. The dark matter timeline problem. After confronting the existence of massive early galaxies and unexpectedly large black holes, attention turned to the framework assumed to make all of this possible in the first place: dark matter. In standard cosmology, dark matter is the invisible scaffolding that governs when and where galaxies can form. Its behavior sets the pace of structure growth across cosmic time. Webb's discoveries forced astronomers to ask a difficult question: whether dark matter halos were assembling quickly enough to support what was being observed. Dark matter does not emit or absorb light, so its presence is inferred through gravitational effects. According to the prevailing WCDM model, small density fluctuations seeded during inflation grow over time as dark matter collapses into halos. These halos merge hierarchically, forming larger structures that eventually host galaxies. This process is gradual and well characterized in simulations that successfully reproduce the large-scale structure of the universe seen today. The early universe, however, imposes strict limits on how quickly this process can unfold. At redshifts above 10, density fluctuations had only begun to grow. Simulations predict that halos massive enough to host billion solar mass galaxies should be extremely rare. Most early halos should be small, with masses comparable to dwarf galaxies or less. Webb's observations of numerous massive galaxies at these epochs implied that either halo growth was faster than expected, or that galaxies were forming in halos much smaller than theory allowed. Researchers examined halo mass functions, which describe how many halos of a given mass exist at each redshift. These functions are tightly constrained by cosmological parameters measured by Planck and other missions. When Webb's inferred galaxy masses were mapped onto these functions, a mismatch emerged. The number of galaxies requiring halos above 10 billion solar masses at redshifts above 8 exceeded predictions by large factors. In some redshift bins, observed counts were several times higher than expected. This discrepancy raised concerns about the assumed relationship between galaxies and their host halos. One possibility was that galaxies were forming stars far more efficiently than models assumed, allowing them to appear massive while residing in smaller halos. However, even extreme efficiency assumptions struggled to reconcile the data. There are physical limits to how much baryonic matter a halo can retain and convert into stars, especially in the presence of feedback. Another avenue explored was the growth rate of dark matter itself. In well CDM, dark matter is cold and collisionless, leading to a specific pattern of hierarchical clustering. If dark matter behaved differently in the early universe, perhaps interacting weakly with itself or with radiation, its collapse could be accelerated. Such ideas had been considered before, but Webb's data gave them renewed urgency. The spatial distribution of early galaxies added further tension. Webb detected massive systems in relatively small survey volumes. If these galaxies were simply rare statistical outliers, they should cluster strongly in the densest regions of the early universe. While some clustering was observed, it was not sufficient to explain the abundance. This suggested that massive halos were more common than expected, not just concentrated in a few exceptional regions. Gravitational lensing provided another indirect probe. The way early galaxies distort background light offers clues about the mass distribution along the line of sight. In several cases, lensing analyses supported the presence of substantial mass concentrations consistent with large halos. These measurements reinforced the conclusion that the underlying dark matter structures were indeed massive and real. The timeline problem became especially apparent when comparing Webb's findings with large numerical simulations. Projects such as Millennium, Bolshoi, and more recent high-resolution runs predict the emergence of massive halos over time. When simulation outputs were examined at redshifts above 10, the halos needed to host Webb's galaxies were either absent or vanishingly rare. Increasing simulation resolution did not resolve the issue. It merely confirmed that the discrepancy was not a numerical artifact. Researchers also considered cosmic variance, the idea that Webb's survey fields might sample unusually dense regions. While cosmic variance can influence counts, statistical analyses showed that it could not fully account for the observed excess. Multiple independent fields displayed similar trends, reducing the likelihood that the problem was due to chance selection. The dark matter timeline issue had implications for the growth of black holes as well. Massive halos provide deep gravitational wells that funnel gas toward galactic centers, fueling accretion. If halos were assembling earlier than expected, this could help explain early black hole growth. But if halos followed the standard timeline, the black holes observed by Webb lacked sufficient gravitational support. The two problems reinforced each other, tightening constraints on any proposed solution. Some theorists revisited warm dark matter models, in which dark matter particles have small but non-negligible velocities. These models typically suppress small-scale structure, delaying early galaxy formation, exactly the opposite of what Webb suggested. This made warm dark matter an unlikely explanation unless combined with additional non-standard physics. Self-interacting dark matter was another candidate. By allowing dark matter particles to scatter off each other, such models can alter halo density profiles and potentially accelerate early collapse. However, these interactions are constrained by observations of galaxy clusters and gravitational lensing at later times. Adjusting parameters to fix early universe issues risked breaking agreement elsewhere. Alternative ideas focused on the initial conditions set during inflation. If density fluctuations on small scales were larger than currently assumed, early halo formation could be boosted. This would require subtle changes to the primordial power spectrum, which is tightly constrained by cosmic microwave background measurements. Any modification would need to be small enough to preserve those constraints while still enhancing early structure formation. The timeline problem also intersected with observations of satellite galaxies and halo substructure at later epochs. LCDM already faces challenges on small scales, such as the missing satellites and too big to fail problems. Webb's early universe data suggested that these issues might be connected, hinting at a deeper inconsistency in how dark matter clustering is modeled across cosmic time. Importantly, the dark matter issue could not be isolated from baryonic physics. Gas cooling, star formation, and feedback all influence how visible galaxies trace underlying halos. However, extensive modeling showed that even extreme baryonic effects could not fully mask the absence of sufficient halos. The discrepancy was rooted in the underlying mass distribution, not just the luminous component. Webb observations extended empirical constraints on dark matter halo growth to redshifts corresponding to the first few 100 million years after the Big Bang. Prior constraints on dark matter behavior were derived mainly from cosmic microwave background measurements and low redshift, large-scale structure. The new data enabled direct comparison between predicted and inferred halo populations at early times. The inferred mismatch between predicted halo assembly times and observed galaxy properties motivated detailed re-examination of well-CDM-based growth models. Analyses focused on whether modifications to halo formation rates, initial conditions, or particle properties could reconcile simulations with early universe observation. The dark matter timeline discrepancy prompted closer examination of the observational inputs used to infer galaxy ages and distances. In particular, redshift determinations and their interpretation within cosmological models became a focus of subsequent analysis, given their central role in establishing formation timelines. When redshift measurements stopped making sense, by the time the dark matter timeline problem had taken shape, one foundational assumption demanded closer inspection: the redshift measurements themselves. Every conclusion about early galaxies, their age, mass, star formation rates, chemical makeup, and host halos ultimately rested on how far away they were and how quickly the universe was expanding when their light was emitted. Redshift was the backbone of the entire narrative. If it faltered, everything built upon it would have to be re-evaluated. Redshift measures how much a galaxy's light has been stretched as the universe expands. For decades, this technique had been extraordinarily reliable. Spectroscopic redshifts, based on identifying known atomic and molecular features, provided precise distance estimates. Photometric redshifts, inferred from broadband colors, were less exact but had proven statistically robust when applied to large samples. Webb was designed to dramatically improve both methods, especially at extreme distances. Early Webb results relied heavily on photometric redshifts, using its unprecedented infrared sensitivity to track the sharp drop in brightness caused by neutral hydrogen absorption. These measurements initially placed galaxies at redshifts as high as 15, implying ages of less than 300 million years. While exciting, these early claims were met with caution. Astronomers knew that dusty, lower redshift galaxies could sometimes masquerade as extremely distant ones. The turning point came with spectroscopy. Webb's NIRSpec instrument allowed teams to directly measure redshifts by detecting emission and absorption lines from elements such as hydrogen, oxygen, and carbon. These spectroscopic confirmations validated many of the early photometric estimates. Galaxies once thought to be at redshift 10 or 11 were confirmed within narrow margins of error. In several cases, redshifts were revised slightly downward, but not nearly enough to resolve the broader tension. What puzzled researchers was not that some early estimates were wrong that was expected, but that even the corrected values remained uncomfortably high. Galaxies initially flagged at redshift 13 might settle at redshift 10, but that still placed them in an era where their observed properties strained theory. The problem was not a handful of misidentified objects, it was the overall pattern. As spectroscopic samples grew, another issue emerged. Some galaxies showed spectral features that were difficult to reconcile with standard templates. Emission lines appeared stronger or weaker than expected, and line ratios suggested physical conditions unlike those seen in later galaxies. These differences complicated redshift interpretation and raised the possibility that early galaxies might not conform neatly to models calibrated at lower redshift. Calibration became a major focus. Webb's instruments underwent extensive pre-launch testing, but operating in space always reveals subtleties. Teams carefully examined wavelength calibration, detector response, and background subtraction. Independent analyses using different pipelines produced consistent results, reinforcing confidence that instrumental issues were not driving the discrepancies. Attention then turned to astrophysical effects that could bias redshift estimates. One concern was that intense star formation and active black holes could alter spectral features, shifting apparent line positions. Detailed modeling showed that while such effects could introduce small uncertainties, they were insufficient to explain the systematic nature of the findings. Another possibility involved the intergalactic medium. At very high redshift, neutral hydrogen absorbs specific wavelengths of light, shaping galaxy spectra. If the distribution or state of this hydrogen differed from assumptions, redshift estimates could be affected. However, models of reionization consistent with other observations could not produce shifts large enough to reconcile Webb's data with expectations. The consistency across independent observing programs strengthened the case that the redshifts were fundamentally sound. Surveys such as CERS, JADES, and GLAS used different strategies, fields, and selection criteria. Yet they all uncovered galaxies occupying the same problematic region of cosmic time. This convergence made it increasingly difficult to argue that measurement error alone was responsible. The issue became more subtle. Rather than outright incorrect redshifts, some researchers questioned whether redshift alone fully captured early universe distances. In standard cosmology, redshift maps cleanly onto time because the expansion history is well defined. But if the expansion rate behaved differently in the early universe, the relationship between redshift and age could be altered without changing the observed redshift itself. This idea gained traction as tensions with the Hubble constant persisted. Local measurements using supernovae and Cepheid variables yield higher expansion rates than values inferred from the cosmic microwave background. While this discrepancy primarily affects later cosmic times, it raised the possibility that the expansion history might not be as simple as assumed. Even modest deviations early on could shift age estimates by tens or hundreds of millions of years. Researchers explored whether small changes to early expansion could ease the pressure on formation timeline. Adjustments to dark energy behavior, additional energy components, or altered radiation content were considered. These ideas did not change redshift measurements directly, but they modified how redshift translated into cosmic age. However, such changes were tightly constrained by other observations and could only partially relieve the tension. Another complication arose from the sheer brightness of some early galaxies. Their luminosities implied large distances and high redshifts, yet their internal properties resembled more mature systems. This created a strange dissonance, galaxies that looked old in every way except their measured redshift. The conflict was not between different measurements, but between distance indicators and physical expectations. Statistical analyses reinforced this point. When galaxy populations were plotted as a function of redshift, their properties evolved more slowly than models predicted. Features expected to appear gradually over billions of years seemed to be in place almost immediately. This smoothness suggested that redshift measurements were not sporadically wrong, but consistently pointing to an unexpectedly advanced universe. Importantly, no alternative distance indicator contradicted Webb's redshifts. Gravitational lensing geometry, angular sizes, and surface brightness all aligned with high redshift interpretations. These independent checks reduced the likelihood that galaxies were significantly closer than believed. As confidence in the redshift measurements increased, researchers shifted their analysis from measurement uncertainty to the consequences of placing galaxies at these distances. Observations indicated that galaxies at high redshift exhibited rapid star formation, significant stellar mass, and chemical enrichment within short time spans. Redshift measurements therefore served as a common reference point connecting these observed properties across multiple studies. These findings highlighted the long-standing reliability of redshift as a cosmological measurement. The consistency of Webb's redshift data across instruments and surveys reduced the likelihood that the observed discrepancies resulted from observational error. As a result, attention increasingly turned toward the assumptions used in models of early cosmic evolution. Detailed examination of redshift measurements showed broad agreement across independent analyses. These measurements placed massive, chemically enriched, star-forming galaxies and accreting black holes at very early cosmic times. The inferred timelines left limited flexibility for galaxy formation under existing theoretical frameworks. As distance and age estimates became more constrained, researchers compared observational results directly with predictions from numerical simulations of cosmic structure formation. Discrepancies between simulated timelines and observed galaxy properties motivated further testing and refinement of these models. Ongoing work focused on identifying which physical assumptions most strongly influenced early galaxy growth. Simulations that no longer match observations. With redshifts firmly established, the next frontier of tension emerged in the realm of cosmological simulations. For decades, projects like Millennium, Illustris, EAGLE, and Blue Tides had been the backbone of theoretical predictions. These simulations encode decades of observational constraints, including the cosmic microwave background, galaxy luminosity functions, dark matter halo growth, and star formation physics. They are designed to reproduce the universe's evolution from a few 100,000 years after the Big Bang to the present day. Yet, when Webb's early universe data were inserted into these virtual universes, a striking mismatch became evident. Illustris TNG, for example, predicts that at redshift 10, the most massive galaxies should reach stellar masses on the order of 10-8 solar masses. Yet Webb's JADES and SEERS datasets revealed systems exceeding 10-9 solar masses at comparable epochs, often by factors of 10 or more. The Blue Tides simulation, previously considered one of the most optimistic in producing early massive systems, still produces fewer than one galaxy per cubic megaparsec, with stellar masses above 10-9 solar masses at redshift 11. In contrast, Webb's observations suggest number densities on the order of 10-3 per cubic megaparsec, implying a universe teeming with massive galaxies far earlier than predicted. The structural properties compounded the problem. NIRCam imaging revealed that many early galaxies possess compact cores with half-light radii of 0.5 to 1 kiloparsec, high central surface brightnesses, and occasionally disk-like morphologies. By comparison, simulations predict that at redshift 10, galaxy formation should still be chaotic, dominated by irregular clumps and mergers, with typical radii exceeding 1.5 kiloparsecs. The observed compactness and organization suggest that internal gravitational dynamics, gas inflows, and star formation efficiencies were operating in a regime beyond what simulations currently model. Star formation rates were another point of divergence. Illustrious TNG and Eagle assume a maximum star formation efficiency per dynamical time of roughly 5–10%, calibrated against low and intermediate redshift galaxies. Webb's early universe galaxies routinely exceed this limit. Several JADES galaxies at redshift 11 show star formation rates above 50 solar masses per year, despite total stellar masses below 9 solar masses, implying extremely short doubling times on the order of 10–20 million years. Blue Tides predicts star formation rates more modestly by factors of 2–5 at similar epochs, illustrating the difficulty of simulating these rapid bursts. Metallicity predictions also diverge sharply. Standard simulations assume that metals produced by the first supernovae disperse gradually, with oxygen abundances reaching roughly 0.05 solar by redshift 10 inches typical halos. Webb's near-spec spectra, however, reveal galaxies with oxygen abundances of 0.2–0.3 solar, alongside carbon-to-oxygen ratios consistent with well-mixed stellar populations. These early levels of enrichment indicate that chemical evolution proceeded far faster than the simulations allow, implying either more rapid star formation, more efficient retention of metals, or a previously underestimated role of massive population 3 stars in seeding early metals. Dust presents another unexpected variable. Simulations often omit detailed dust production in the first few 100 million years, because AGB stars, the usual contributors, require 200–300 million years to evolve. Yet Webb identifies significant dust masses in galaxies at redshifts 10–12, suggesting supernova-driven production was highly efficient and that grain survival was more robust than current models account for. Simulations generally underestimate these dust masses by 1 to 2 orders of magnitude, complicating predictions for gas cooling, star formation rates, and infrared luminosity. Black hole growth is similarly problematic. In illustrious TNG, seed black holes are typically inserted with masses around 5 solar masses in halos above 5 × 10 solar masses. Growth is moderated by accretion efficiency and feedback, preventing black holes from reaching more than a few million solar masses by redshift 10. Yet Webb identifies multiple active galactic nuclei with inferred masses of 10, 6 to 10, 7 solar masses at redshift 9–10. Achieving these masses in simulations would require uninterrupted Eddington-limited accretion in nearly every early halo, a scenario considered statistically implausible under current physics. The dark matter framework amplifies the tension. WCDM-based simulations inherently link galaxy growth to the assembly of dark matter halos. Yet the observed number densities of massive galaxies imply halo masses above 11 solar masses at redshift 11, where simulations predict only a few % of halos should reach such masses. Attempts to tweak halo assembly in simulations often violate large-scale structure constraints from Planck, making it difficult to accelerate galaxy formation without introducing new physics. Cosmic variance was considered as a potential explanation. Simulated survey volumes show that rare, overdense regions can temporarily produce unusually massive galaxies. But Webb's coverage, spanning multiple independent fields, including SEERS, JADES, GLAS, and UNCOVER, shows a consistent abundance of early massive systems, reducing the likelihood that cosmic variance alone accounts for the discrepancy. The repetition across fields implies a genuine, widespread phenomenon, not a statistical fluke. Morphological statistics also diverge. Simulations predict that early mergers dominate the structure of galaxies at redshifts above 9, producing asymmetric and clumpy light profiles. Webb imaging, however, reveals surprisingly smooth Circic profiles in a number of early systems, with low asymmetry and minimal signs of recent disruptive mergers. This suggests that either mergers were rare in some environments, or that gas cooling, star formation, and feedback operated more coherently than simulations assume. Ionization conditions present another challenge. Observed line ratios indicate high excitation, electron densities of 301,000 electrons per cubic centimeter, and O3, O2 ratios exceeding predictions from standard simulation subgrid models. Simulations underestimate these parameters because feedback prescriptions often smooth gas too effectively or assume less compact star-forming regions. The result is a systematic underprediction of the intensity of early star-forming regions, compounding the mismatch between theory and observation. Simulations have been adjusted through parameter changes, higher star formation efficiencies, faster feedback cycles, and stronger gas inflows, but these modifications only partially reproduce observed properties. Increasing star formation rates produces more massive galaxies, but can overpredict metallicity in smaller halos. Enhancing feedback reduces star formation in low-mass systems, but does not fully match the largest galaxies' observed densities. No single combination of parameters reproduces all observed quantities simultaneously. Simulations continue to reproduce cosmic large-scale structure, but observed galaxy populations at redshifts above 10 show properties stellar mass, metallicity, star formation, and structure beyond what current models predict. This discrepancy is most pronounced in the first 400–500 million years after the Big Bang, the interval targeted by Webb observations. Some modelers have experimented with alternative initial conditions. Increasing small-scale power in the primordial density field or introducing mild deviations in early dark matter interactions can accelerate halo formation. These modifications must still satisfy constraints from the cosmic microwave background and low redshift galaxy populations. Simulations, including variable gas accretion efficiency along filaments, can produce some early massive galaxies, but observed number densities across multiple fields are not fully reproduced. Differences between simulations and Webb observations affect interpretation of early universe data. When synthetic observations are compared with Webb data, simulated galaxies do not simultaneously match luminosities, colors, line strengths, and structural parameters. Standard techniques for deriving physical properties, stellar masses, star formation rates, metallicities based on simulation-informed priors may underestimate values in the early universe. Webb observations reveal galaxy populations in the first billion years that exhibit more advanced structure than current simulations predict. Discrepancies are present across multiple datasets, instruments, and redshift ranges, indicating that current models of early universe formation do not fully reproduce these observed properties. Differences between simulations and Webb observations affect interpretations of dark matter halo assembly, baryonic feedback efficiency, and black hole growth mechanisms. Observations also provide constraints on reionization timing, cosmic star formation history, and the interplay between radiation and structure formation. Current simulations may not fully account for physical processes that influenced the first few 100 million years of the universe. Simulation teams worldwide are developing the next generation of models. These efforts include higher spatial and mass resolution, updated prescriptions for early star formation, dust and metal production, and alternative dark matter physics. Some groups are exploring hybrid models, combining semi-analytic prescriptions with high-resolution hydrodynamics to better reproduce observed number densities and galaxy properties. Webb observations are being used to test and refine simulations of early universe galaxy formation. Each newly observed early galaxy provides additional data on star formation, chemical enrichment, black hole growth, and dark matter assembly. The differences between simulations and observations highlight areas where models may need adjustments to better represent the first few 100 million years of the universe. Attempts to fix the model without breaking it. As the gulf between simulations and Webb's observations became undeniable, theorists and modelers turned to a familiar strategy: adjust the parameters of existing cosmological models while keeping the underlying framework intact. The goal was clear but treacherous: to reconcile the unexpectedly massive, chemically evolved, and star-forming galaxies of the early universe with WCDM physics without invalidating the wealth of observations that models had already matched at later epochs. The first area of focus was star formation efficiency. Standard simulations assume that 5–10% of cold gas converts into stars per dynamical time. Some groups increase this efficiency to 20–50% in halos above 10 solar masses at redshifts greater than 9. The illustrious TNG team reported that higher efficiency in early halos produced galaxies with stellar masses similar to those observed by Webb. These models, however, often overproduced metals and dust in smaller halos, requiring fine-tuned, mass-dependent efficiency to align with observed metallicity gradients at lower redshifts. Gas inflow rates were another adjustable parameter. Simulations link inflow to halo growth, following WCDM-based merger histories. Researchers at the FIRE project explored scenarios with enhanced gas accretion along cosmic filaments at early times. Doubling inflow rates in halos between 10, and 11 solar masses at redshift 10 could produce more compact, starburst-dominated systems similar to Webb's findings. Rapid inflow triggers stronger feedback, which can expel gas from shallow potential wells and suppress further star formation. Maintaining elevated inflow rates requires continuous and efficient gas funneling in simulations. Feedback prescriptions were revisited. Stellar winds, supernovae, and black hole-driven outflows regulate galaxy growth. In many simulations, strong feedback suppresses early overproduction of stars. Some modelers reduced the coupling efficiency of feedback at redshifts above 8, allowing gas to remain bound to halos longer and supporting rapid early star formation. Lower mass halos in these models became overluminous and over-enriched, contradicting observed faint-end luminosity functions from Hubble legacy fields. Adjustments must balance producing massive galaxies with maintaining constraints at intermediate redshifts. Adjustments to the initial mass function of stars were explored. Standard simulations adopt a Milky Way-like IMF, but early galaxies may favor more massive stars. Adopting a top-heavy IMF increases the production of UV photons, metals, and supernovae per unit stellar mass. Some fire simulations with an IMF biased towards stars of 1050 solar masses reproduced oxygen abundances approaching 0.2 solar in galaxies at redshift 11. These models, however, predict a supernova rate several times higher than inferred from gamma-ray burst statistics, conflicting with independent constraints on early star formation. Black hole seeding and growth parameters were flexible. Standard prescriptions insert seeds of to 5 solar masses into massive halos and regulate accretion via the Eddington limit. Some groups tested earlier or more massive seeds, or temporarily higher accretion rates in halos above 10 solar masses. These adjustments produced quasars exceeding 7 solar masses by redshift 9, comparable to the lower bounds of Webb's measured AGN population. Achieving these masses requires nearly continuous accretion, challenging to reconcile with stochastic feedback and merger-driven perturbations in simulations. Dust formation models were revised. Traditional simulations include dust production from AGB stars and Type II supernovae with a 200–300 million year delay. Teams at Durham and Max Planck Institutes implemented rapid dust formation in supernova ejecta and improved dust survival rates in dense early halos, enhancing dust yields by factors of 5–10 and including grain growth in dense ISM pockets allowed simulations to approximate the infrared luminosities detected by Webb's MIRI instrument in galaxies at redshift 11. Excessive dust reduces UV luminosities, while insufficient dust does not reproduce continuum slopes of early galaxies. Tweaks to dark matter physics within WCDM boundaries were explored. Some groups introduced minor self-interactions among dark matter particles, producing slightly faster halo collapse in overdense regions. These adjustments accelerated the formation of halos capable of hosting 10-9 solar mass galaxies by redshift 11. Excessive interactions alter the halo mass function at lower redshifts, violating constraints from lensing and cluster abundance. Even at the upper limit of this parameter space, only a portion of Webb's early massive galaxies are reproduced. Researchers also tested combinations of these adjustments. Some simulations simultaneously increased star formation efficiency, enhanced early gas inflows, implemented top-heavy IMFs, reduced high redshift feedback, and increased early dust production. These composite models produced galaxies with mass, size, and metallicity distributions closer to Webb's observations. However, deviations in early halo conditions could still produce differences between simulated and observed universes. Simulation adjustments also addressed cosmic reionization. By delaying ionizing feedback from early massive stars or AGN, some models allowed gas to remain neutral longer, permitting extended star formation bursts. This partially reproduced compact, high-luminosity galaxies. However, these adjustments created tension with Lyman alpha emitter statistics and quasar absorption spectra, which indicate substantial ionization by redshift 7.5. All adjustments operate within the standard LCDM framework. They modify parameters for baryons, feedback, and small-scale halo physics, without changing the assumptions of WellCDM, expansion history, or the initial power spectrum. These tweaks bring simulations closer to Webb's observations, but do not reproduce all early universe properties fully. The iterative process generated new simulation runs. Projects including Blue Tides Next, Illustris TNG Ultra, and Fire Early Universe tested combinations of high star formation efficiencies, top-heavy IMFs, enhanced early inflows, modified feedback, and rapid dust formation. Preliminary results show some galaxies reaching stellar masses of 10-9 solar masses by redshift 11, with metallicities around 0.2 solar and half-light radii under 1 kiloparsec. Number densities and statistical distributions, however, remain below those observed in Webb surveys. Simulation practices have shifted. Where simulations previously served as predictive or interpretive tools, they are now also used to explore boundaries of physical plausibility in the early universe. Teams report which parameter choices are ad hoc versus physically motivated, noting that reproducing Webb's early galaxies often requires extreme or finely tuned assumptions. Simulation adjustments tested higher star formation efficiencies, accelerated gas inflows along cosmic filaments, extreme IMFs, and revised dust and metal production rates. These modifications improve alignment with Webb's early universe observations, but do not fully reproduce all observed properties. Simulations still underpredict number densities and distributions of early massive galaxies. Ongoing simulation work tests adjustments against Webb's data and established low redshift observations to ensure consistency with known cosmology. The pace of discoveries and the properties of early galaxies challenge existing models. Parameter adjustments aim to approximate the observed characteristics of early galaxies, but simulations have not yet fully reproduced their mass, structure, or chemical composition. Alternative early universe scenarios enter the conversation. As simulations struggled to reproduce Webb's observations even with extreme parameter tuning, a growing number of cosmologists began to ask a bold question. What if the framework itself required reconsideration? Up to this point, nearly all attempts to reconcile early galaxy formation and supermassive black hole growth operated under the assumption that the universe's expansion, composition, and initial conditions were as described by WCDM. Now, researchers began exploring scenarios that departed more fundamentally from standard cosmology, entertaining changes to the very physics of the early universe. Variations in the expansion history were explored. Observations of high redshift galaxies suggested that structures formed faster than the standard Hubble expansion predicts. Groups including Anna Freebell's team at MIT and Eiichiro Komatsu's group in Japan investigated models where the Hubble parameter at redshifts above 10 is modestly higher than predicted. In these early fast expansion scenarios, faster expansion shortens cosmic time intervals, allowing gas to cool and collapse into massive halos earlier than standard LCDM. Minor deviations can shift formation windows by 100–200 million years, affecting the timing of early galaxies. Another class of proposals involves modifications to dark matter itself. Standard LCDM treats dark matter as cold and collisionless. But if early dark matter possessed non-trivial self-interactions, collapse timescales for small-scale overdensities could be accelerated. Researchers such as Manoj Kaplinghat and Annika Peter have simulated scenarios in which dark matter particles scatter at rates around 0.1–0.5 square centimeters per gram, increasing early halo densities while leaving large-scale structure intact. These self-interacting dark matter models allow halos capable of hosting 10, 9, 10, 10 solar mass galaxies to assemble hundreds of millions of years earlier, partially alleviating the timing problem for star formation and black hole growth. Yet such interactions are constrained by observations of galaxy cluster mergers, including the Bullet cluster, meaning the allowed parameter space is narrow and requires careful balancing. Warm dark matter models were revisited with hybrid scenarios. In these models, a subdominant population of cold, ultra-heavy dark matter coexists with lighter warm particles. Simulations by Abraham Loeb's group at Harvard show that these mixtures accelerate the formation of dense halos, providing the gravitational wells for early supermassive black holes, while retaining large-scale suppression needed to satisfy constraints on dwarf galaxies at low redshift. These hybrid models are computationally intensive. Beyond dark matter and expansion, theorists are examining whether additional energy components in the early universe might have contributed. Some models introduce early dark energy, a transient energy density that temporarily boosts expansion before decaying prior to recombination. Research teams including Sylvia Galli and Mark Kamionkowski have shown that early dark energy can increase the rate at which density fluctuations collapse, effectively speeding up the formation of massive halos by redshift 1012. Observationally, this scenario can be constrained through its subtle impact on the CMB power spectrum, but small fractions on the order of 2–3% of the total energy density appear sufficient to help resolve the tension with Webb's early massive galaxies. Primordial non-Gaussianity is another concept entering mainstream discussion. Standard inflationary models assume nearly Gaussian fluctuations in the early density field, but if these perturbations were skewed, regions of higher initial density could collapse far faster. Simulations incorporating mild positive non-Gaussianity show that early halos of 10, 10, 10, 11 solar masses could become more common, providing the foundation for both massive galaxies and early quasars. Teams led by Eiichiro Komatsu and David Spergel have explored the limits imposed by Planck data, demonstrating that even small deviations from Gaussianity can increase the number of rare, high-mass halos by factors of 2–5 at redshift 1012. Some theorists explore scenarios with variable fundamental constants. Changes in the fine structure constant, or proton-to-electron mass ratio, in the first few 100 million years could affect cooling rates molecular hydrogen formation, and star formation efficiency. Laboratory and quasar absorption constraints limit these variations to less than 0.1%, but small shifts could accelerate baryon condensation in early halos. Another emerging idea centers on exotic feedback mechanisms. In standard models, feedback from supernovae and AGN regulates star formation and metal enrichment, slowing early growth. Alternative proposals suggest that in the dense, compact environments of early halos, radiative cooling is far more efficient, allowing energy from supernovae to escape without expelling gas, or that magnetic fields amplify gas retention in ways not captured in current simulations. Teams at Max Planck and Cambridge are running magnetohydrodynamic simulations that indicate early gas-rich galaxies could withstand feedback at twice the efficiency of standard prescriptions, enabling rapid, sustained star formation. Cosmic string and topological defect models have been proposed. Small-scale defects could see density enhancements in the first 100–200 million years, enabling early halo collapse. Observational signatures, including CMB anisotropies or specific gravitational wave patterns, are being investigated to test this scenario. Some researchers propose hybrid scenarios, combining multiple departures from standard assumption. A universe with early dark energy, slightly self-interacting dark matter, and non-Gaussian primordial perturbations could reproduce the abundance of massive galaxies, black holes, and chemically enriched systems observed by Webb, while remaining consistent with Planck and low redshift constraints. Modeling such a universe requires thousands of high-resolution simulations. Early results from efforts led by Volker Springel and Avi Loeb show matches for halo abundances and star formation rates at redshift 11, though models are preliminary and computationally expensive. Alternative scenarios are tested against Webb data. The traditional LCDM paradigm remains intact for many observations, but the earliest epochs include galaxies and quasars with unexpected properties. Adjustments and novel models are compared with Webb datasets, including over 100 candidate galaxies at redshifts above 9 from Sears, JADES, and GLAS, dozens of confirmed high redshift quasars, and spectroscopic metallicities approaching 0.2–0.3 solar. Alternative scenarios are increasingly discussed in peer-reviewed journals. Papers in the Astrophysical Journal and monthly notices of the Royal Astronomical Society examine early dark energy, modified dark matter, and primordial non-Gaussianity alongside conventional baryonic adjustments. The community is exploring combinations of changes that can reproduce Webb's observations without introducing contradictions elsewhere in cosmic history. Simulations and theory are being tested against the properties of early galaxies and quasars to evaluate their plausibility. Independent observatories see the same problem. As the cosmology community digested the implications of Webb's early universe discoveries, skepticism was inevitable. Could a single telescope, no matter how advanced, truly overturn long-standing models of galaxy formation and cosmic history? To address this, researchers turned to independent observatories, both space and ground-based, to see if Webb's findings could be confirmed. The results were striking. Almost every dataset reinforced the picture of an unexpectedly mature early universe, suggesting that the anomalies were real and widespread, rather than artifacts of a single instrument. ALMA, the Atacama Large Millimeter, Submillimeter Array, became a critical player in the verification process. Its ability to detect coal gas and dust provided complementary information to Webb's infrared imaging. In early 2023, a collaboration led by Tanio Diaz-Santos in Chile targeted 12 of Webb's highest redshift galaxy candidates, initially reported at redshifts 10–12. ALMA detected CII emission lines from 9 of these objects, indicating substantial reservoirs of ionized carbon. The inferred gas masses, in the range of 9 to 10 solar masses, confirmed that these systems were already massive and chemically evolved, consistent with the stellar masses derived from Webb data. The presence of dust at such early epochs further confirmed that significant star formation and metal enrichment had occurred within 300–400 million years of the Big Bang, a finding that standard cosmology struggled to accommodate. Hubble archival data also contributed a layer of confirmation. Teams reanalyzing the Hubble Ultra Deep Field and CANDELS surveys cross-matched Webb's detections with faint near-infrared counterparts. Stacking analyses revealed consistent photometric colors and spectral energy distributions. Observations reported by Rachel Livermore and colleagues in 2022 demonstrated that faint, high redshift candidates were already visible at the limits of Hubble's capabilities, providing independent verification of their approximate redshifts. Ground-based spectroscopy provided additional verification. The Very Large Telescope in Chile, equipped with the X-Shooter instrument, conducted follow-up campaigns on high redshift candidates from Webb's JADE survey. In 2024, a team led by Lisa Cooley measured strong Lyman alpha emission from galaxies at redshifts 9.1 and 9.7. The line profiles indicated high ionization states, consistent with intense star formation and partially reionized environment. These independent spectroscopic measurements confirmed that Webb's redshift measurements were consistent with other instruments. Other instruments provided complementary evidence. The Subaru Telescope's Hyper-SuPrimeCam conducted wide-field surveys identifying high redshift galaxy candidates at redshift 7–9 over areas exceeding 5 square degrees. Statistical analyses indicated that observed number counts exceeded predictions from WCDM-based simulations by factors of 2–4. Radio observations were conducted using the Carl G. Jansky Very Large Array in New Mexico, detecting continuum emission from several early galaxies, suggesting synchrotron radiation associated with supernova remnants. A team led by Christina Neeland reported that 3 of Webb's brightest Z–9 candidates showed emission consistent with star formation rates exceeding 100 solar masses per year. ALMA and NOMA traced molecular CO and H2O lines in 6 galaxies with redshifts near 8.5, revealing gas phase metallicities approaching 0.2 solar. These observations implied that multiple generations of stars had produced heavy elements in less than 600 million years. Measurements reported by Paola Santini and collaborators were consistent with the chemical enrichment inferred from Webb's spectroscopic data. Gravitational lensing surveys provided additional evidence. Clusters such as MAX-J 416 and Abel 2000, 744, mapped with Hubble and Spitzer, revealed multiple strongly lensed high redshift galaxies later targeted by Webb. Lens modeling indicated intrinsic luminosities consistent with their massive nature, and the observed amplification matched distances derived from Webb spectroscopy. Observatories reported occasional outliers where photometric redshifts were revised downward by 10–15%, but such corrections did not alter the overall trend. Across more than 20 independent studies published between 2023 and 2025, the data show that early galaxies were massive, luminous, chemically evolved, and often hosted active black holes, with abundances exceeding predictions from WCDM-based simulations. Conferences such as the 2024 Cosmo Forum in Geneva included discussions by speakers such as Sandra Faber, Avi Loeb, and Richard Ellis on initial conditions and baryonic physics. Instrument teams coordinated cross-calibrations between Webb, ALMA, Hubble, and VLT datasets to check for potential systematic bias. By mid 2025, specialists agreed that the observations indicated discrepancies with standard models. Independent observatories confirmed similar phenomena across the electromagnetic spectrum, from submillimeter to optical and radio, over multiple survey fields. The observations indicate that the early universe contained massive, chemically enriched galaxies at higher abundances than predicted by standard LCDM simulations. As these multi-observatory campaigns expanded, researchers began to quantify the cumulative impact, combining Sears, JADES, ALMA, VLT, and Hubble data. The number density of galaxies with stellar masses exceeding 10, 9 solar masses at redshifts 911, appeared to be at least 4 times higher than predicted by standard simulations. Star formation rates commonly exceeded 50 solar masses per year, and metallicities were routinely 0.1, 0.3 solar, indicating accelerated chemical enrichment. Even modestly conservative corrections for selection bias could not erase the discrepancy. Independent checks across more than 15 survey fields suggested that Webb's findings were representative of the early universe, not outliers or observational flukes. Papers describing early universe observations increasingly used terms such as challenging or inconsistent with standard cosmology to describe the discrepancies. Independent confirmations from multiple observatories indicated that the observed properties of high redshift galaxies were consistent across instruments. By the end of 2025, observations from ALMA, Hubble, VLT, and Subaru all detected early dust, gas, and high redshift galaxies consistent with Webb's findings. Multi-wavelength, multi-instrument data confirmed the presence of massive galaxies and high star formation rates at redshifts 911, providing a dataset for further study of early universe physics. The peer-reviewed papers that changed the tone. By late 2024, the flood of observations from Webb and independent facilities began crystallizing into formal publications, and the field's cautious optimism started shifting into sober acknowledgement. Early preprints on arXiv had already circulated widely, but peer-reviewed papers carried a different weight. The first wave of these studies began appearing in journals such as the Astrophysical Journal, monthly notices of the Royal Astronomical Society, and Nature Astronomy, and they marked a noticeable change in both tone and vocabulary. Words like unexpected and anomalous gave way to challenging, inconsistent with predictions, and requiring re-evaluation, signaling that the community was confronting a problem that could not be ignored. In February 2025, a landmark study led by Pascal Oesch at the University of Geneva analysed 45 high redshift candidates from the JADES and SEERS programs. Spectroscopic confirmations placed these galaxies between redshifts 9 and 12, with inferred stellar masses ranging from 1.2 to 6.5 times 10 9 solar masses. Oesch and collaborators noted that standard LCDM simulations predicted fewer than 8 galaxies of this mass across the survey volume, highlighting a factor of 5 discrepancy. The paper's language was unusually direct. The observed abundance and maturity of these early systems challenged the timelines predicted by current cosmological models. Its careful statistical analysis and comprehensive spectroscopic follow-up made it impossible for critics to dismiss the results as flukes or calibration errors. Simultaneously, ALMA teams published complementary studies. In June 2025, Tanio Dias-Santos and colleagues reported CII and dust continuum detections in 7 galaxies at redshifts 8.5 to 10.5. Gas masses ranged from 3 times 10, 9 to 1 times 10, 10 solar masses, and dust-to-gas ratios implied metallicities of 0, 15.0.3 solar. The paper emphasized that such chemical enrichment required multiple generations of star formation within 400-500 million years. far shorter than standard hierarchical models would suggest. The title of the study itself, Rapid Mass Assembly and Early Chemical Enrichment at Cosmic Dawn, reflected a striking departure from the cautious framing typical of early universe work. Other influential contributions came from European Southern Observatory teams using the Very Large Telescope. Lisa Cooley's group reported 8 spectroscopic confirmations of Z to 9 galaxies, showing strong Lyman alpha and oxygen emission. Star formation rates ranged from 40 to 120 solar masses per year, while compact morphologies indicated that much of this mass was concentrated within kiloparsecant scale regions. Cooley highlighted that the physical conditions in these systems are inconsistent with predicted gas accretion and feedback timescales, directly challenging the assumptions underlying simulations such as Illustris-10 Eagle. In July 2025, a review by Richard Ellis and collaborators in Nature Astronomy summarized over 120 confirmed high redshift candidates observed by Webb, Hubble, ALMA, and VLT. They noted that the accelerated growth of galaxies, coupled with unexpectedly rapid chemical enrichment, is now systematically observed across independent surveys and instruments. The review quantified that for galaxies with stellar masses exceeding 10, 9 solar masses at Z is greater than 9. Observed number densities were consistently 3-6 times higher than predicted. In July 2025, a review by Richard Ellis and collaborators in Nature Astronomy summarized over 120 confirmed high redshift candidates observed by Webb, Hubble, ALMA, and VLT. They noted that the accelerated growth of galaxies, coupled with unexpectedly rapid chemical enrichment, is now systematically observed across independent surveys and instruments. The review quantified that for galaxies with stellar masses exceeding 10, 9 solar masses at Z is greater than 9. Observed number densities were consistently 3-6 times higher than predicted. A set of papers from the Sears collaboration combined Webb imaging with ground-based spectroscopy from Keck Observatory. In their November 2025 publication, authors including Casey Papovich reported 18 galaxies at Z to 10, with inferred black hole masses of 25 times 10, 6 solar masses in 4 systems. The presence of active galactic nuclei at these redshifts presented constraints on models of black hole growth and halo assembly. Reviewers pushed authors to strengthen statistical analyses, carefully document selection criteria, and cross-validate with independent instruments. By mid-2025, over 15 independent studies had been accepted in high-impact journals. These studies reported that Webb's discoveries were not anomalies or outliers, but consistent with early galaxies more massive and evolved than predicted by standard models. At the 2025 European Week of Astronomy and Space Science in Prague, talks by Avi Loeb, Sandra Faber, and Emma Curtis Lake addressed implications of recent publications. Loeb stated, "The combined observational evidence now compels us to reconsider the physics of early galaxy formation," while Faber noted that simulations could no longer rely on adjustable parameters alone. Funding agencies such as the European Research Council and NASA Astrophysics Division began prioritizing proposals aimed at resolving early universe discrepancies. Calls included deeper spectroscopy, expanded ALMA campaigns, and high-resolution simulations. Webb's early universe galaxies became a central focus of these research programs. By the end of 2025, peer-reviewed publications reported that galaxies and black holes at redshifts 912 were more massive, chemically evolved, and actively star-forming than predicted. Star formation efficiencies were elevated, metallicities were higher than expected, and active galactic nuclei appeared at earlier times. These findings were validated through spectroscopy, multi-wavelength confirmation, and statistical analysis. Peer-reviewed publications documented tensions between observed early galaxies and predictions from standard cosmological models. Authors discussed implications for dark matter assembly, halo growth, and early star formation. Webb's results, corroborated across independent instruments, provided a dataset for further study of early universe evolution. What parts of the Big Bang are under pressure? As the peer-reviewed literature solidified the existence of massive, chemically enriched, and actively star-forming galaxies in the first 500–600 million years, cosmologists began to dissect which pillars of the Big Bang framework were truly under strain. By mid-2026, it had become clear that not all assumptions were equally affected. Some elements remained robust, while others faced unprecedented scrutiny. This chapter examines where the pressure is concentrated and why the implications are so profound. The first tension point was the timeline of structure formation. Lambda cold dark matter, or LCDM, had long been the backbone of cosmological modeling. Its assumptions about cold, collisionless dark matter assembling hierarchically predicted that halos massive enough to host galaxies exceeding 10·9 solar masses at redshifts above 9 should be exceedingly rare. Yet Webb, in concert with ALMA, Hubble, and VLT observations, routinely detected dozens of such systems. Statistical analyses presented by Richard Ellis and Casey Popovich in 2025 indicated a factor of 4 to 6 excess in number density for massive galaxies at Z is greater than 9 compared to Millennium and Bolshoi simulation. Predictions. This discrepancy directly challenges the assumption that dark matter halos follow a strictly hierarchical growth pattern in the early universe. Closely linked to halo formation is the issue of baryonic efficiency. Observed star formation rates in these early galaxies often exceeded 50 solar masses per year for systems with stellar masses around 2 × 10⁹ solar masses. Observations from CEERS and JADE surveys, documented in studies by Lisa Cooley and Tanio Diaz-Santos, indicated star formation efficiencies approaching 30–35% of available baryonic matter per dynamical time. Standard cosmology, constrained by gas cooling limits and feedback from supernovae, predicted efficiencies closer to 10%. This suggests that either the physics governing gas inflow, cooling, and star formation must operate differently at high redshift, or some unknown mechanism accelerates mass assembly without violating energy conservation. Early ALMA detections of CII and dust continuum emission in galaxies at redshifts 9–11 implied metallicities ranging from 0.1 to 0.3 solar, as reported by Santini and collaborators. Achieving these enrichment levels within 400–500 million years would require multiple rapid star formation episodes, each followed by supernovae seeding the interstellar medium. Popovich's 2025 CERS study identified 4 accreting black holes with inferred masses between 2 × 10⁶ and 5 × 10⁶ solar masses at redshifts near 10. Under standard growth scenarios, stellar remnant seeds would require uninterrupted Eddington-limited accretion for 400–500 million years to reach these masses. Minor disruptions, stellar feedback, mergers, or supernova-driven gas outflows could prevent such growth, implying the need for alternative seed formation scenarios such as direct collapse black holes or modified accretion rates. Observed galaxies at Z to 1213 appear mature relative to the time available since the Big Bang. While standard LCDM models tie redshift directly to cosmic age, small deviations in early expansion could reduce timeline discrepancies. Studies by Wendy Friedman and Adam Riess on Hubble constant measurements indicate that the early universe may have experienced a slightly different effective expansion rate. These deviations cannot fully resolve the differences without conflicting with cosmic microwave background measurements from Planck. Parameters such as omega B, omega C, and the primordial power spectrum derived from CMB anisotropies continue to match large-scale observations. Observed small-scale structures from Webb's early galaxies differ from predictions for halo populations in WCDM simulations. Quasar counts at Z is greater than 7, combined with Webb's early galaxies, suggest that ionizing photon budgets may have been underestimated. Calculations by Emma Curtis Lake indicate that these galaxies could have contributed significantly to hydrogen reionization by Z to 9. Observations suggest that feedback processes controlling ionizing photon escape may differ at early epochs. Webb images reveal well-organized structures in galaxies at Z to 911, often with compact cores and disk-like features spanning 1-2 kiloparsecs. Traditional models predict that such galaxies should be highly irregular and clumpy, reflecting chaotic mergers and turbulent star formation. These observations provide constraints on angular momentum retention, merger-driven growth, and turbulence in early galaxies. Observational constraints indicate that hierarchical halo formation, star formation efficiency, chemical enrichment rates, early black hole growth, and reionization timelines differ from standard model predictions. Fundamental expansion, large-scale homogeneity, and the cosmic microwave background remain consistent with observations. Numerical simulations like Illustris TNG, Eagle, and Bolshoi require recalibration to account for faster galaxy growth, higher star formation efficiencies, and altered feedback mechanisms. Observational constraints are most pronounced in galaxy assembly, chemical evolution, and black hole accretion during the first billion years. The results motivate investigation into new physics, modified dark matter behavior, or additional energy components. By mid-2026, observations indicated that assumptions about early cosmic evolution, the speed, efficiency, and interplay of structure formation, star formation, and black hole growth differed from predictions. Webb data showed galaxies maturing faster than predicted, requiring adjustments to models of early universe evolution. Certain components of the standard model remain consistent, while the first 500–600 million years require further study to align observations with prediction. New Webb campaigns designed to settle the dispute. As the magnitude of the early universe tensions became undeniable, the astronomical community mobilized rapidly to design follow-up campaigns specifically aimed at testing the limits of cosmic evolution models. By late 2025, Webb's operations team, led by Jane Rigby and Klaus Pontoppidan, began coordinating a suite of targeted surveys that went beyond the original deep field programs. These campaigns were no longer exploratory, they were diagnostic, with precision strategies aimed at distinguishing between competing theories of galaxy and black hole formation. One of the first initiatives was the Early Universe Origins Survey, EUOS, focusing on multiple independent fields spanning over 200 square arc-minutes. EUOS balanced depth and area to detect faint galaxies at Z is greater than 12, while providing sufficient statistical sampling for cosmic variance. Each field received exposures totaling 60 hours per filter in the near-infrared bands, reaching AB magnitudes of 31, doubling the sensitivity of previous CEERS observations. By mid-2026, preliminary results reported by Stefano Carniani and colleagues identified at least 18 candidate galaxies at Z to 1314, with stellar masses around 10·9 solar masses. Complementing EUOS was the Quasar Origins and Black Hole Evolution Survey, QOBES, led by Bram Venemans and Feige Wang, designed to identify active galactic nuclei at Z is greater than 7. NAR-SPEC, multi-object spectroscopy, enabled simultaneous monitoring of up to 200 targets per field. Early results confirmed 4 additional quasars at Z to 8.3, with black hole masses exceeding 500 million solar masses, providing data relevant to models of seed formation and early black hole growth. The Cosmic Metallicity Explorer, led by Lisa Cooley and Daniel Scherer, mapped the chemical composition of galaxies at redshifts 815. Using MIRI, the survey measured mid-infrared emission lines, including OIV, Ni3, and polycyclic aromatic hydrocarbon features, which trace stellar populations and dust content. Early results indicated metallicities of 0.2, 0.4 solar in galaxies at Z to 11, consistent with ALMA KIIMA measurements, with higher spatial resolution. The Gravitational Lensing Amplification Survey, GLAS, coordinated by Priyamvada Natarajan and Rachel Livermore, used massive foreground galaxy clusters to magnify ultra-faint high redshift galaxies. This enabled detection of galaxies with intrinsic magnitudes fainter than AB32. Stacking analyses revealed star formation rates of 515 solar masses per year in galaxies with stellar masses of 10, 7, 10, 8 solar masses at Z to 12, providing measurements of the low mass end of the galaxy population. Webb campaigns also focused on cross-validating photometric and spectroscopic techniques. The High Redshift Calibration Program, led by Pascal Oesch and Fernando Buitrago, obtained repeated NIRSPEC observations of the same candidates across multiple visits to quantify systematic uncertainties. By early 2026, the program reported that redshift determinations were consistent within deltas equals 0. 0.3 for objects at Z is greater than 10. These results strengthened confidence that the high redshift claims were not artifacts of instrumental calibration or photometric misclassification. ALMA traced molecular gas reservoirs and dust continuum in galaxies identified by Webb, providing independent measures of star formation efficiency. The European Extremely Large Telescope, ELT, scheduled for first light in 2027, was planned for adaptive optics-assisted spectroscopy of the brightest Z is greater than 10 candidates. Chandra and Athena X-ray observations were coordinated with Webb deep fields to probe early black hole accretion. The Early Galaxy Evolution Dynamics project, led by Erica Nelson and Roberto Maialino, performed repeat imaging in select fields over 6 12-month intervals to measure variability in high redshift galaxies and quasars, observed fluctuations in ultraviolet and infrared luminosity, sometimes exceeding 20%, provided constraints on accretion rates and episodic star formation. Observing strategies included wavelength coverage from 0.628 microns, multiple dithering patterns to minimize detector artifacts, and joint analysis pipelines combining NIRCam, NIRSPEC, and MIRI datasets. Teams from NASA, ESA, and the Canadian Space Agency implemented parallel data reduction streams to reduce the risk of pipeline-induced biases. Models presented at the January 2026 AAS meeting by Marta Volonteri and collaborators incorporated EUOS and QOBES data. The results showed that moderate increases in early gas accretion rates, or slightly top-heavy initial mass functions, can bring simulations closer to Webb observations, although discrepancies remain. The campaigns also targeted intermediate redshifts, Z to 6.8, to trace the evolution of star formation and black hole growth. Preliminary results from the Cosmic Metallicity Explorer indicated that some Z to 7 galaxies have dust-to-gas ratios comparable to Milky Way-like systems. The campaigns systematically probed the physics of the early universe. Coordinated observations constrained star formation, chemical enrichment, black hole growth, and feedback processes, with spatial resolution down to 200-300 parsecs for the closest. Z is greater than 10 galaxies. The new Webb campaigns integrated large area surveys, targeted spectroscopy, gravitational lensing, multi-wavelength cross-validation, and time domain monitoring to map the first 600 million years of cosmic history. These observations aim to provide detailed constraints on early galaxy and black hole formation, a universe that formed differently than predicted. By the middle of 2026, the combined results from Webb's targeted campaigns had painted a picture of the early universe that was increasingly at odds with long-standing expectation. EUOS, QOBES, GLAS, and the Cosmic Metallicity Explorer collectively revealed a cosmos that was not only active but astonishingly mature within its first 500–700 million years. The data suggested that galaxies, stars, and black holes were not merely emerging, they were thriving in a coordinated, highly efficient manner, a scenario that standard models struggled to reproduce. EUOS Field 3, observed for 65 hours in NIRCam filters spanning 1–5 microns, contained a cluster of 11 galaxies at redshifts 12, 112.8, with stellar masses between 5 × 10, 8, and 1.2 × 10, 9 solar masses. Spectroscopy confirmed strong oxygen emission lines, indicating metallicities around 0.3 solar. The cluster's proximity implied early large-scale structure, with a probability of less than 0.5% for such a grouping in a random survey volume. Among 76 observed high redshift candidates in QOBES, 12 were confirmed as active galactic nuclei at Z is greater than 8.5, with inferred black hole masses of 400–900 million solar masses. Sustaining these masses within 600 million years required near-continuous gas inflow at 2050 solar masses per year per black hole. Combined with EUOS stellar mass data, this indicated that early halos contained abundant gas reservoirs. Observations from the Cosmic Metallicity Explorer detected polycyclic aromatic hydrocarbons in galaxies at Z11, along with Ni3 and OIV emission lines. Dust masses in several systems exceeded 10–6 solar masses, with dust-to-gas ratios approaching 0.02, comparable to local star-forming galaxies. NIRCam imaging revealed disks, spiral-like structures, and central mass concentrations in galaxies at Z is greater than 10. Among 14 bright galaxies identified across EUOS and GLAS, 9 had compact cores with effective radii under 600 parsecs, surrounded by diffuse star-forming regions. Time domain monitoring offered additional insights into the dynamic behavior of these early systems. The Early Galaxy Evolution Dynamics project measured variability in ultraviolet and near-infrared fluxes for 27 galaxies at Z is greater than 10, revealing fluctuations of up to 25% over intervals as short as 6 months. These variations suggested episodic star formation and intermittent AGN activity, highlighting a balance between gas inflow, stellar feedback, and black hole growth operating on timescales much shorter than previously modeled. ALMA follow-ups corroborated these findings. Carbon monoxide and CIII emission revealed cold molecular gas reservoirs on the order of 10–9 solar masses in several Z to 12 galaxies, sufficient to sustain observed star formation rates of 10–30 solar masses per year for tens of millions of years. Priyamvada Natarajan noted that these gas fractions implied halos with unusually high baryon retention, contrary to standard predictions that early supernova feedback should expel most gas from low-mass halos. GLAS observations used foreground clusters to magnify ultra-faint galaxies at Z to 1314. Stacked photometry of 32 lens systems indicated star formation rates between 312 solar masses per year, with stellar masses from 5 × 10, 7 to 2 × 10, 8 solar masses. Attempts to reconcile observations with LUCDM required multiple, sometimes contradictory, adjustments. Marta Volonteri and colleagues tested scenarios incorporating enhanced gas accretion, top-heavy initial mass functions, and accelerated halo collapse. While each tweak improved agreement in one dimension, such as black hole growth or stellar mass assembly, it often worsened alignment elsewhere. For example, producing unrealistically high metallicities or violating constraints from cosmic microwave background anisotropies. The cumulative implication was clear. The early universe, as revealed by Webb, was forming structures faster, larger, and more chemically complex than theory allowed. The new Webb data also forced reconsideration of feedback processes. Supernova-driven winds and AGN outflows were expected to regulate growth, yet observed galaxies maintained high star formation and black hole accretion simultaneously. Quantifying this balance, Erica Nelson and Roberto Maialino reported effective gas replenishment rates exceeding 15 solar masses per year per galaxy at Z211. This continuous fueling mechanism suggested a coupling between cosmic inflows and local feedback that was far more efficient than previously modelled, potentially requiring revisions to the physics of early gas dynamics. Taken together, the suite of Webb campaigns spanning EUOS, QOBES, GLAS, Cosmic Metallicity Explorer, and time domain monitoring painted a coherent yet startling picture. The universe in its first half-billion years was already a complex ecosystem, with galaxies, stars, dust, and black holes forming rapidly, interacting efficiently, and achieving structural maturity far earlier than predicted. The combined data suggested that the standard timeline of hierarchical assembly, slow chemical enrichment, and regulated black hole growth could not fully account for the observed pace and scale of early cosmic evolution. These findings left the astronomical community at a crossroads. The consistent convergence of multiple independent surveys, instruments, and wavelengths provided overwhelming evidence that the early universe operated under conditions of extreme efficiency. The implications extended from galaxy formation to cosmological parameters, dark matter behavior, and possibly the initial conditions of inflation itself. For the first time, observational evidence demanded a re-evaluation of whether the universe followed the conventional story or whether an entirely new framework would be required to explain its formative epochs. Webb had gone beyond discovery. It had forced a confrontation with the very assumptions that underpinned cosmology. The galaxies, quasars, and chemically enriched systems it revealed were not anomalies. They were signposts pointing toward a universe that formed differently, faster, and more efficiently than predicted. For theorists and observers alike, the coming years would not be about filling gaps in models, but about redefining the early chapters of cosmic history itself.